Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired software engineer for Microsoft going back to the MS-DOS and Windows 95 days. And today, I have the rare privilege of being joined by Dave Cutler, the chief architect and designer of what we know today as Windows. As someone who's gone on to design 3 successful operating systems in a row, from RSX 11 to VMS and then Windows, Dave has few, if any, peers in the industry. And if he did, he'd outwork and outlive them anyway, as he's still actively coding as a senior technical fellow at Microsoft at the age of 81. Dave was the recipient of the 2007 National Medal of Technology and Innovation at the White House, and in 2016 was honored as a fellow at the Computer History Museum. Now, with all of his achievements and honors, you might think I'd be tempted to put him on a pedestal like digital royalty, but I found him as approachable today as when he was just Dave C., my boss's boss's boss. So please join me in welcoming Dave to the shop. Let's get on with the interview. Let's see, might as well start with something interesting. There's a legend that when Windows NT first shipped, that a gift was sent to Sun by the team. I don't know many details about it, and nobody's willing to tell me very much about it. Is there anything you're willing?
Well, we decided that when Scott McNeely was kind of mealy-mouthed, and there were some other people around that were a little bit that way too. Another one was Lee Reiswick at IBM. So we decided somebody, and I don't know who it was, it might have been Callie Wilson, who was the admin for the group, found these black cardboard coffins, and they were about 2 feet long. So we decided that we would send Scott McNeely and Lee Reiswick a coffin, and we would put a special message in it, and some guy found these like birthday cards that play a song.
Oh, yeah.
So he found a birthday card that played the Death March, dun, 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 dun. And so we sent one of these to Lee Reiswick, and we sent one to Scott McNeely. And Scott McNeely, at the time, Sun was running ads with they had a dog, and the dog's name was Network. And Scott McNeely is reputed to have brought Network on the stage at one of his talks with a fire hydrant, and had the dog go over and urinate on the fire hydrant, and it said Microsoft on the fire hydrant. So we got some fake dog-do and put in the box. And I think we got a license, or a retail license or package for, I don't know, it was Sun OS or they had two. They had Sun OS and what the other one was. And so we sent that. We had both of these. We had hand delivered, so we know that they actually showed up.
Right.
We had a third one, and I forget who we were going to sell. The third one might have been going to Larry Ellison or somebody else. But that one never went off. And I have. Did you go to the 21st anniversary?
Yeah, I did.
I showed the video.
That must be where I've seen it, because I haven't.
I showed the video. We decided. There's a little side story here too. I hope we don't get distracted here and this goes on too long, because I like to tell stories. We did a video. We decided we're going to video this, and we're going to show it at the Whim on Friday. So we got somebody to come in and video it, and I did a couple of mock presentations for Lee Reiswick and Scott McNeely. And we were going to show these on Friday at the Whim. Well, this is the same time that the DOJ was suing Microsoft over DOS.
Right. And
on Tuesday, I told Alchin that we were. Oh, in fact, what happened was Alchin was coming by as we were videoing this stuff, and somebody's out in the hall. I think it was Dave Thompson, said he's kind of giggling, and Alchin wants to know why he's giggling, and Thompson said, "Hey, come in, look at what we're doing." So Alchin came in, and this is the greatest thing in the world. He wants to sign it. And everybody signed a card. He wants to sign it. Well, this is on Tuesday. On Wednesday, Bill comes out with a company-wide memo that says we're going to be nice people from now on, and we're not going to disparage our competition or anything. So Alston comes in on Thursday and tells me we can't show this at the whim and we can't send these. And I said, geez, that's too bad, Jim. We already sent them. So they made it out. But so anyway, for the 21st anniversary, I dug up the videotape.
Okay.
And we had it put on a DVD and showed it at the 21st anniversary. That's what you saw was one of those presentations.
Cool. I'll have to see if I can find a copy of this.
It was a black box, and I think we delivered it with red roses.
Okay.
It was great.
So was it always operating systems for you? No urge to make a living in job control language or anything like that?
Well, what happened was, I came back after doing this model, and this model was never really very satisfying because, the people at Scott Paper, sort of didn't really care. And this is sort of a PR thing. It's like DuPont's, offering this service to help them. And, we talked to the plant manager and, they'd sit in their chairs and, and we asked them for a particular problem and they wanted to know what the run length should be to maximize the yield, because you have startup problems. You have startup time and you have shutdown time where the Zarks weren't perfect, and the Zarks were never perfect anyway. The Zarks had a big skin on them, which turned out to be a problem because they had to peel the skin off.
Right.
So anyway, I decided that I was going to go to work somewhere else. And my boss in this math and stat group had left and went to Union Carbide. So I queried Mark Union Carbide about whether or not they might have a job for, I could get a job. And I actually interviewed with them in New York City. And they sent me off to Kokomo, Indiana to interview for a job in Kokomo, which was a plant that made Hastelloy, which was a steel used in submarines, which is very highly corrosion resistant. And Kokomo, Indiana there may be one town that was worse, which was Gary, Indiana, but Kokomo was pretty bad. Anyway, about the same time, I interviewed at the engineering department at DuPont. Engineering department was not an operating department. It was a department that built all their chemical plants. DuPont actually designed and built their own plants, all their own chemical plants, because they didn't think that they didn't want to give away any of their secrets, for one thing, and they didn't think anybody else could do what they could do, right? So they had a group there that was called the Real-Time Systems Group, and they built some real-time systems for some of the operating plants. So I thought that was a pretty good job. But their offer came back, was kind of weak, or I thought it was weak. And I accepted the job in Kokomo, only to find out about a week later that the job at the engineering department was paying much more than I thought it was. And so I sent all this stuff. They sent me tickets and everything. And I sent it all back and said, I'm not taking your job. What a career decision that was. I would have ended up being a COBOL programmer, and I'd probably still been there in Kokomo.
Yeah, probably.
So anyway, I went to the engineering department, this real-time systems group. And they had built some systems for the textile fiber plants. There's one in Tennessee. Well, they were all over the South. And I can't remember exactly what any of the systems did, but anyway, the computers were Bunker Ramo 340s. The Bunker Ramo 340 was a 28-bit machine. It was a very interesting machine. Anyway, I got into that group, and the first thing I did there was they wanted to build automatic analysis of Instron tensile testing. Instron is a machine that basically you pull things apart with.
Okay.
And they have a bunch of strain gauges that look at what's going on with what you're pulling apart to see where the yield points are and everything, and they chart this all out. And then somebody has to look at it and say, oh yeah, this is the modulus was with the yield point, and they had a bunch of other things with the tensile strength and all that. So we're going to automate all this. So I basically wrote the program that did that, I wrote the program that collected all the data, and it was a real-time program, and it ran, I think we ran every 100 milliseconds or something like that to get data. 100 milliseconds was fine for this stuff because you're pulling this apart at not anything that's a really rapid speed. Right. It's sort of like this. And so I was in this group, and I worked on that project, and so again, I'm bored. There's nothing to do. I get to a point where, I'm not bored because of the work stuff. I'm bored because this is an engineering services department, and they have to wait until somebody says, we want you to do something. Right. And then there's a whole bunch of stuff about proposing the project and what they're going to do. Well, the same 1107 was right down the hall from me, and they had a group of about 3 people that supported that. And so I went down and said, hey, you guys need any help? And they said, yeah, we can get you to do something. So I started work on Exec 2, which was the 1107 operating system at that time, which was a batch system. Okay. But it was fast. It was really fast. We could run batch systems faster than, really fast. And it was a fast machine. And then eventually it went to the 1108. So that's where I really got into the operating system part. And every night at 5 o'clock, we kick off the operators, and we get the machine for 2 hours. So in those 2 hours, we had to run all the experiments we cooked up for the day, all our test code and whatever. Right. And of course, everything was, like debuggers. There's no debuggers. There's switches on. There's lots of switches on the 1107, and there's a way we could halt instructions and things like that. So it was kind of it was very interesting. A lot of interesting concepts in that system that I sort of carried forward in VMS. So I worked on that, and then the next thing I did was the experimental station wanted to automate the analysis of all their Instron system stuff. The other one was just for plants with a bunker Ramo. Okay. So we actually were going to build a big computer system to do this, and we ended up. This is again this is in the real-time systems group now because I was just loaned to the other group, and so we end up with a dual PDP-10 system, sharing memory, and we had a PDP-8 front end for all of the terminal input, and then we ran, I think we ran analog lines in conduit for like 3,000 feet, a long distance, a lot of noise, but a long distance. And in the dual PDP-10, we ran TOPS 10 on one of them, and then we ran another system that the group that I ran developed.
So they shared memory?
Shared memory, yeah. Systems? Yeah. Shared memory, I think we had 32 K words, 32 K words of shared memory, and then I think each one of them had 16 K of non-shared memory. So we could dump data very fast between the two systems directly. And then we had a dual interrupt system, or dual interrupt capability to interrupt back and forth. So from there, I went to digital. And of course, I went to digital to work on operating systems. So that's what I worked on at digital.
How long were you at digital before you started on RSX?
Well, I immediately started on RSX 11C.
So that's one of my questions. Didn't they not have people internal? Why were they pulling external people in to start brand new operating systems?
Well, I was really hired to work on OS 45.
Okay.
And at that time, OS 45 is sort of in this embryonic state where it's this pipe dream of Dave Stone, who was a graduate of MIT and worked on Multics. So the big thing about the 45, the PDP-10 was like a microsecond machine. The 1145 was a 300 nanosecond machine. And he had and the PDP-10 was sold as a time-sharing system. Some of the time-sharing service bureaus had PDP-10s.
Right.
All the colleges had PDP-10s. People loved the PDP-10. So he had great visions that we're going to build this system, or a lookalike system, on this new computer called PDP-11 because it was 3 times as fast. Well, he had one thing that he didn't really think about a bit enough, and it's the biggest single thing that obsoletes architectures is the number of address bits. 16 bits just wasn't enough.
Right.
So in the OS-45 was going to be, at that time, we were going to have a subsystem. It was the real-time subsystem and the batch subsystem and the time-sharing subsystem. It sort of sounded like some of the IBM 360 systems at the time. IBM had a dozen operating systems probably for the 360. So we're working on all the concepts, and we're hiring people for the team. And this project has been over in IPG, which is Industrial Project Group, for like a couple of years, trying to get the PDP-11 to just do terminal emulation. This is, that's all. Just core only, terminal. And they're working on this thing called R611C, and their main architect is this guy from Foxborough. Do you know who Foxborough is?
Don't the Patriots play there?
Yeah. Actually, Foxborough was in Foxborough, and it was a process control company.
Okay.
So they produced custom process control systems. And so they hired this guy from there who was absolutely terrible. He may have been really okay with the kind of process control hardware that they were sequencers or whatever, but he was really trying to build something that was an operating system that ran multiple tasks and context switched and all that stuff. And this is only like, how much code is this? I'd be surprised if it was more than 10,000 lines of code. So it was small. It was not very big. And they'd been working on this 2 or 3 years, and IPG was desperate. So they said, geez, would you go work on this in your spare time? And I said, well, sure. So I ended up working on that. And we eventually did release that. I think I worked on that about a year, and it was terrible. It was horrid. I mean, at the time, if you took today's customers and tried to superimpose them on the products of that time, they'd all walk away.
Right.
They'd just walk away. I mean, R611C was probably capable of controlling your doorbell, right? But not much more.
Right.
And I don't know, I don't know how many they sold or what they did. I did another little offshoot of that actually brought the disk into the picture, but it never was anything that, had a command capability or anything like that. You just basically, you had a set of sources that you customized to build whatever your application was.
Right.
Whether it was like, probably mainly reading switches somewhere, and maybe reading switches and then output to switches, but not much more than that.
And what kind of hardware was that on?
PDP-11.
Okay.
11.
So when you started VMS, was it always self-hosted on VAX prototype hardware, or did the code start on a PDP-11 platform, or?
Well, it turned out, actually, the VAX had a PDP-11 mode.
Right.
And we developed something that was very similar to WOW 64, where you could run PDP-11 programs on VAX. So, that side of the operating system, all the utilities and all that, we took from R611M right out of the distribution and ran them. But the development on the system, we had a group that produced an emulator, a hardware emulator. And It was microcode. It was a microcoded hardware emulator, and I can't remember how. It was not really that slow. I mean, it wasn't fast, but it wasn't slow either. So the very embryonic work, scheduling and memory management and that sort of stuff went on that, and we only had one of those on that one machine, and of course all of the tools and everything ran on R611M, which was 16 bits. We were building stuff on the 16. Well, most of it was on the 16-bit system. So the assembler ran on the 16-bit system, producing 32-bit relocatable code.
Okay.
The linker, however, ran on PDP-10. The linker was written in Bliss. You know what Bliss is?
I've heard of it, but never up close.
Bliss was a language that was invented by CMU, and its claim to fame was it was go-to-less. And it never really caught on. It was very error-prone. Everything was an L value, and you had a specific operator to dereference it, and everything had to be explicitly dereferenced. Like if you're looking at C, you look at a statement that says A equal B plus C. Well, you have an implicit dereference of B and C, and you have an implicit reference of A on the left-hand side, which is a store through whatever the value of A is, which is its address. In Bliss, you had to have a dot in front of all those. So there's a very strict dichotomy between what is the L value and what is the R value.
Right.
Very error prone. It was a dot. And of course, without a go-to, all your logic got kind of inverted. Everything is a while, so that you can leave. You can exit the while. It's somewhere in the middle. So anyway, they had developed this language, and there was a compiler on the PDP-10, and we did a cross compiler on the PDP-10 for VAX, so that we could do the linker. The debugger was always also written in Bliss on the PDP-10, but all the rest of the development occurred on the 11, on R611M, on 1170, by the way. And we could run, I would say, 12.5 users on R611M on a 70. It's amazing what we could do in 64 kilobytes of memory.
Right.
I mean, amazing. We had compilers, linkers, I mean, all that stuff. And today, you link something that says "Hello World," it's a megabyte. It's probably not a megabyte, but it's close to a megabyte. It's huge. So anyway, that's how that all got bootstrapped. And then eventually we got one of the early prototypes. I think it was Proto 6. And we decided, and this is the same thing we did in NT, in Windows, was that we're going to eat our own dog food. And as soon as we got to the point where we could actually run reliably enough on Proto 6, actually it was Proto 3, it's Proto 3, we could run on Proto 3, then we had our offices, and the machine is like, it's like our offices are here and the machine is sitting over there. And if the machine bug checks, about 3 or 4 of us get up, walk over to the machine, sit there in the debugger for a while and figure out what it is, reboot the system, go back to our office, fix the bug, update the system, reboot, and then go on.
Right.
And that's what we did. That's the way.
Having everybody self-hosted on the same system kind of instill a quality thing, because you're bringing down everybody if you bring down anybody, pretty much.
Well, there was only one piece of hardware,
right.
Period. So there was no way that you're going to host. You can't. They could still run assemblies and things like that on RSX11M. They could still develop the linker on the PDP-10, right? We just couldn't develop the things that ran in the operating system, all right? But we brought all, since this layer, which was equivalent to WOW64, was called the AME, was the Application Migration Executive. Much thinner layer than WOW64 is, much thinner. It basically looked like a PDP-11.
Right.
And, it loaded up the programs and started them, and they ran. And the file system was compatible. It was files. We took the R611M file system to VMS, which was called Files 11, and we just re-implemented it. I don't think we really did. We didn't do anything that was, an enhancement really. It was just a re-implementation of the same thing. So the file system worked. We didn't have to do anything special for that. The file names were the same. In those days, there was one character set. It was ASCII, period. There's no other character sets. There was no graphics, so we didn't have to worry about graphics. Basically worrying about disk drivers, tape drivers, terminal drivers. We had network stuff. We were implementing DDCMP, which was Digital's protocol that preceded. Well, it didn't actually precede TCP/IP because TCP/IP was an outgrowth of DARPA, and that actually occurred before DDCMP. But we were also developing SNA and BiSync, which was IBM's remote terminal protocol for 2780s terminals.
Okay. I've heard the VMS shipped with 0 bugs. Does that...
On the day we shipped VMS, there were 0 known bugs. That didn't mean there were no bugs, because there were bugs. But there's a big difference between shipping a system with 20,000 known bugs that some program manager said, well, we've looked at this and it doesn't meet the bar. That used to just drive me just batty. Right. I wanted every bug fixed, every bug. And it gets so depressing as we're going through the Windows release, the NT releases, where we have this war room every morning, and you fix 200 bugs in a day. Next day, there's 200 new bugs every single day for months. All right, but anyway, we made a real effort to fix every bug that we knew about before we said, okay, we'll ship this. And I know there was a last-minute bug. We had a race condition in a channel hole or handoff that occurred in one of the disk drivers that we fixed like in the 11th hour, but there were 0 known bugs at the time we shipped.
But you were schedule driven as opposed to, you didn't have to make Christmas for deck, obviously, or that kind of thing.
No, but the thing that happened there, I guess you could really say we were schedule driven because, the success of the company was selling hardware. It wasn't selling VMS.
Right.
And we couldn't sell the hardware without the operating system to run on it. So as soon as manufacturing is ready to start pumping these systems out, now you got inventory, you got customers that bought machines, you want to have the software to run on them. And,
right.
And in fact, we shipped some systems to customers that were early, sort of like the early adopter program. We had 2 customers that we actually gave early VAX hardware to, and to help us develop things. One was Schlumberger. Schlumberger was putting VAXs in semi-tractor trailer trucks and carting around the U.S. taking data on oil well.
Oh, really?
Right? They were, they send a instrument bundle down the casing, and I don't know, they set off explosions or what they did, and then get all that data. They collected all that VAX and then process it. So Schlumberger was one, and the other one was related to the naval. It wasn't the Naval Academy, but it was some other naval organization. And we had 2 software support specialists at each one of those customers, and they would sort of be the people that would take the updates. We update the system, not as often as we update the systems at Microsoft when we're doing development, which is basically every day. But, we get to a point, we operated in what we call base levels, which was, when we planned at the beginning, we set out what the base levels were, and this is the base level of functionality that we try to reach by a certain point, and we wouldn't go on to other stuff until we reached that point. So there's various base levels. So as these came out, people would get upgraded, and they only got the functionality was in the base level. So, and customers generally were at the other end of that, where they get much more capability. But, there's things, I don't know, we probably ran for a year where the system was actually usable. We did the development on that system.
Right.
And it was reliable enough that it didn't crash that often. As far as stress on it, we didn't really probably stress it that badly because, there's, 24 to 30 people sitting around, plinking on keys.
Right.
Now we had better terminals then. We had CRT terminals with keyboards that didn't require a pound of force to push down the keys. You ever push down a key on a JSR-33?
Yeah. The round post.
There weren't any speed typers in those days.
No. After VMS, you worked for a bit on an embedded system or a real-time control system of some kind?
After VMS, I worked on the PL1 compiler.
Yeah, how did you get into compilers and why? And how do you pick up compilers as a...
Well, there's always this interest in this magic that compilers did. And I always wanted to do a compiler or find out about a compiler. And at the end of the VMS project, Release 1, I decided that there was a project that one of the commercial divisions of Digital wanted to have a PL1 compiler. And so they were looking for somebody to develop the compiler, and all the language groups didn't want anything to do with this at all. They were Fortran and COBOL. Not anything else. The basic stuff was all over on the PDP-11. So we bought a front end from a company from Boston, and the guy, I can't remember what the name of the company was, but the guy's name was Bob Fiberhouse, and it was a PL1 subset front end. And so we bought that, and then we had to develop the back end. And I developed the code generator for the back end. And
what did the front end compile to?
An intermediate language.
Okay.
In fact, all the compilers do that these days. There's several phases of the compiler, and each one does, its job and moves on. But we ended up doing the back end we did on VAX, and the front end work that we did at MIT on Multics. And we tried to work from Tewksbury, Massachusetts, remotely with Multics, and it was a non-starter. You could not run half duplex. It was so slow. So we ended up, we had this tape shuttle, and we do the stuff that we needed to do to the front end on the system at MIT, and then put it all off on tape, bring the tape up to Tewksbury, which was maybe 10 miles away, read the tape, and then we'd have input to feed into our back end, which knew what the format of all this stuff, and the outcome of that would be object code, which then we could run through the linker to produce programs. So that's how we developed PL1. So we did a C compiler also with the same back end. It was a very different back end. It wasn't, it was not, elegant. It really wasn't elegant. A lot of it was done in a language we called TBL. And TBL just stood for table, and it was basically a byte interpreter. Because the compiler is so full of function calls. I mean, the density is so high that you run this interpreter, and the interpreter has a bytecode with implied operands. So, if you're going to generate, if you know what the input for the front end is, you have these records that are operands and all kinds of different records, and you can think of each one of these bytecodes as being a processor for that kind of particular type of operand or maybe that record, or maybe it's some sub part of that, some variable reference, or building a symbol table thing or something. So a lot of it was written in that. And then, of course, we also did an optimizer, which I was very interested in optimized code because the early PDP-11 compilers were threaded code. Threaded code was like byte codes, only it was 16 bits rather than 8-bit byte codes. And that's basically what it was.
Okay.
And that's what they compiled to. And then we had these interpreters that ran. So the original Fortran compiler was threaded code. Anyway, I got interested in the optimization. And what really drove me about the optimization was how good a code the 1108 could put out. The Fortran compiler for the 1108 was written by CSC, Computer Sciences Corporation, and it was fast and it was just unbelievably good code. Of course, it might not look so good now, but in those days it looked really good. It ran really well. So I was very interested in optimization. Spent a lot of time on optimization and a lot of time on register allocation. And then I left. I decided, actually, one of the guys that I worked with said there was this guy in California that worked for Lawrence Livermore that had worked on the Shiva Nova project. Shiva Nova is laser fusion. And this is, we're talking circa 1980.
A while ago, yeah.
They're still working on that.
Yeah, 20 years away still.
Yeah, it's like, and so he had been one of the people that was instrumental in convincing the people at Livermore that they had to have a special language developed to write the software to control the lasers for the Shiva Nova project. It was called Praxis. So, like a lot of these things in the government, you know, they got through this thing and got the compiler, and it's funded by the government, so it's public. So he decides he's going to start a compiler company. So I got talked into joining this company with him, and there was 4 of us from digital and 2 from his company. And so I was going to leave. I was already to leave. And Gordon Bell is up in arms. He doesn't want me to leave. So he says, well, you know, what can we do to get you to stay? And I said, I don't know, but I said, I got to get away from here. There's too much bureaucracy here. This is in Massachusetts. And the digital had grown from a company that was like such a great place to work. It was engineers building products for people that were engineers and really liked them.
Right.
And into an atmosphere of you know, all these business people coming in and all these business plans, and no longer, Ken Olson's thing was do what's right for the customer. And it was kind of became, you know, do what's right to make the most money or whatever. And we were very ill prepared for all of the organization and the people we hired and everything. So it got very hard to work. So I said, well, I have to be somewhere remote. He said, well, we'll put you anywhere. We'll put you anywhere you want to go. And I said, well, no, I'm going to do this. Well, this fell apart. We all put in $2,500, and this guy that was going to be the president had a wife that had a calligraphy company, and he contracted her to do our business cards. He blew our whole $7,500. He just blew it all away, and I was so mad about that. I said, that's it. I'm not doing this.
Right.
So,
probably a bad sign.
So Gordon comes back and says, you know, what do you want to do? And I said, well, I want to move somewhere else. He says, well, you go anywhere you want to go. He said, the only thing that I have as a restriction is I want you to go somewhere that's close to university. So I said, well, I have some preconceived notions about where I don't want to go. So I don't want to go to the southeast. I don't want to go anywhere like in Washington, D.C. or any of that area. I don't really want to go to Mid-America. I grew up there. Probably not Phoenix, maybe the Southwest, not maybe the West Coast. So off we go to the West Coast to look at potential places, and we go. Of course, we have a whole group of people now from digital have to jump into this. I can't just go with my group of people and we pick out a site.
Right.
We have to have the real estate people come with us, right? Because they got to get the best deal. And so we go to Sacramento. That's a non-starter. We didn't go to Santa Rosa. They wanted us to go to Santa Rosa, but Santa Rosa would have been a non-starter too. You know, that's sort of north of San Francisco. And at that time, I don't know how much is there now. I think there is some stuff there, but we did go to Portland. I really like Portland. And we went to Seattle. And I remember we were flying into Seattle. Have you ever flown into Ireland?
No.
Ireland, you can't believe how many shades of green there are. I mean, Ireland, you fly in there, it's just all these different shades of green. It's just beautiful. So we're flying into Seattle, and it's just, I mean, it's raining, but it looks really nice. And so she's like, this is a great place. So we decided we're going to start an engineering organization, and University of Washington is next door. So we're going to start an engineering organization there, and what we're going to have as a charter is to develop chip-based system software. And this was at a time where VLSI was just getting started at a large scale, and Digital had great visions that they're going to build one-chip VAXs. And we needed a set of software to run on these really cheap one-chip VAXs that we're going to populate everywhere. So we ended up in Bellevue with about 12 people, and we're going to produce basically a little real-time system for that. And it was called Vaxilon, and it was not a very good system, but it was one of the first systems where we tried out a lot of things that we hadn't tried before, because everybody thought they were great things to do, like drivers in user mode, everything being message oriented, everything's messages, and when you send messages, you unmap it in the sender, and when the receiver receives it, we map it in the receiver. And it was the first system that we did was multi-threaded. So it was multi-threaded. And the other thing, it was multiprocessor.
Okay.
So this is the first multiprocessor, multi-threaded system. And I had some bad experience with customers with some of the features of RS611M and VMS. We had in Windows, we had things called, the names changed, called APCs, which were asynchronous, asynchronous procedure call, APCs, asynchronous procedure calls. In RS611M and VMS, they were called ASTs. They were asynchronous system calls. So they were like interrupts. Well, interrupts in user mode does not work. People just don't get that. So we decided that we should control things much better in this system. So we had a lot of user mode level scheduler controls. You could disable context switching and all sorts of stuff. And stuff like, we'll make it so that we can guarantee that you won't run 2 threads in your program at once. And you know, right after we did it, the first thing that people say is, why didn't you allow this, right? It's like, anyway, we did ship that system, and we had a few customers. One of the customers we had was a company called Cadex. You remember Cadex?
No.
Cadex was an offshoot of the company that made PageMaker.
Aldus?
Aldus, it was. It was an offshoot of Aldus. and they were building some kind of a document control system. And they were a customer, and so we worked with them. Anyway, that's the system, and partway through that system, we look around the company, and there aren't any single chip VAXs, none. So we say, well, geez, we need a small VAX, a small cheap VAX. So the company started a project called MicroVax. And we decided we'd build one. So we built the first MicroVax at Deck West. Deck West was the name of the place. And my contribution to that was I wrote all the microcode for the whole thing.
Really?
Which was a real experience. And I don't have a copy of it. I'm I'm really upset that I don't have a copy of the microcode, but I think it would have been interesting to go back and look at it.
Yeah.
It was 4K by 30 bits. The microword was 30 bits wide. It was 40 bits wide. It was 4K by 40. And it was 5 8-bit proms. That was the microstore.
Okay.
So we built MicroVax 1 and shipped that. And then shortly thereafter, we did come out with a one-ship VAX, which was called MicroVax 2. And so anyway, that was the end of that story.
Sort of a naive question on that. When you've got these old machines with these huge machine words, if you think of the Huffman encoding of instructions, there's going to be instructions that are tiny that don't need anywhere near 40 bits.
No, but the 40 bits is the micro machine. It's not the instruction set.
Oh, okay.
The instruction set is VAX. So what users deal with and what programmers deal with is they think it's a VAX. It is a VAX. In fact, all the VAXs were microcoded. None of them were. In fact, none of the machines today are really hard-coded or hardwired except the ARM processors are hardwired, and the RISC-V ones are too.
Okay.
And there's probably other, ones we don't even know about. The Army has something somewhere, whatever. But all the machines are microcoded. And the microcode on the 780 is like 99 bits wide or 100 bits wide. It's very wide. And so having a wide micro instruction is so that you don't have to do any decoding of vertically encoded fields in the microword. You can just take the bits right out and jam it into the hardware. You don't have to run it through any kind of a ROM or anything that actually takes it from its value. Say it's 0 to 7. That would be it's 8 different bit patterns. But the bit patterns are not, 4 bits. The bit patterns are 8 bits.
Right.
All right, so it's going to take those bits and cry them out. So the wider micro instructions allow for more parallelism, and there's more bits to tweak hardware in parallel.
Okay. So before we get to Microsoft, there was one thing I wanted to ask you about DEC, and that was, I may have the story wrong, but it sounds like before you decided to either move to Deck West or move to Microsoft, you basically shopped yourself back to your own employer to say, what am I worth on the market? Is that a summary of how it went? Or?
Well, actually, there was a little interlude between a couple of the things there that I kind of skipped over, and that was the movement to Deck West.
Okay.
The first thing was really, it wasn't the compiler company. There was another deal, and it was, I got to be really good friends with the program manager for the VAX 750. And he went to work for Intel in Portland. And he worked on the 432 project.
Don't know what that is.
The 432 was Intel's super duper computer or processor architecture. You should wiki this.
This is before the i860, their previous
This is
failed
before
attempt?
this is before the i860. And he worked on that, and he tried to get me to go to Intel. And I said, sure, I'll come out and interview. So I went out and interviewed in Portland. And I would have been working in a group there that was not the 432 group, but it was a group that I think they had a system called RMX16, this was Intel's little real-time system for the 286, I think. And so I interviewed, and they're all favorable, and they want to make me a job offer. And in the 11th hour, they come back and they say, we can't make you a job offer unless you tell Gordon Bell that you're looking for a job and that you interviewed at Intel, because we have a good relationship with Intel. And I said, sure, that's no problem. So I pick up the phone, and I'm in Nashville. Not Nashville. Nashua, New Hampshire. It's Pitbrook Road. I pick up the phone and I call Gordon and say, hey, Gordon, I've been interviewing at Intel, and they told me that I've got to let you know that they want to offer me a job. And I just want to let you know about that. And Gordon says, oh, yeah, well, what's the deal? And I said, well, I'm not really looking for a job. I just like to know what I'm worth. I'd like to have them make me an offer. And Gordon says, oh, okay, that sounds sensible. I hang up. Literally 15 minutes later, I get this call from Larry Portner. Larry Portner is the VP of software engineering at Digital. And he says, Gordon and I would like to have lunch with you today. And I said, really? And he says, yeah. How about lunch, and it's just in Nashua in an hour. And I said, okay. So here comes Larry, here comes Gordon for lunch, and they want to know, what's going on. I said, all I want to know is what I'm worth. And they say, well, geez, you should have said something to us. I said, well, we did VAX, and, that VAX was really, the VMS was really, I worked 7 days a week, 10 hours a day. I said, we got through with that. Across the wall comes like 10,000 shares of stock. And I said, that just didn't seem like a very big reward for all that effort. And, VAX is just this tremendous success, and the company's riding the waves. Oh, well, geez, you're probably right. We probably didn't do very well there. We'll have to do something, but, we really don't want you to take this offer or get this offer from them. Well, it turned out that they actually did cough up some more stock, and I didn't want to work with these guys anyway. And I didn't think Intel was all that sharp, and that sort of blew over. But part of that blowing over was the movement to Deck West and Bellevue. The first go around was the go around where, I'm going to leave the company. And then in the 11th hour, I decide I'm not leaving the company. But this is after Gordon has said, we'll send you anywhere. And this time I said, well, I don't want to go work for Intel, but I really do want to get out of here. So that's when we came out and looked around.
And then after a while at Deck West, you were about a Denny's meal away from Microsoft, if I understand.
I was what?
You were a Denny's meal away from Microsoft with Steve B.
Steve fleeced us.
Did he?
Well, I was leaving. There's a piece missing here, and that is the prison project. Digital in the mid 80s decided to start we started several projects to produce RISC architectures, because we had everybody was building RISC machines. And one of the reasons they're building RISC machines was because they're easy to build at that time. AMD was building these 2901 bit slice chips, and they're 4 bits wide, and they had all the ALU control and all that stuff, and you just gang them together, and presto esto, you have a processor, right? And now all you got to do is design your instruction set and how you're going to feed this thing. So there were a dozen at least RISC machines, and they all claimed to have or RISC in general claimed to have a 2x performance advantage over VAX, because VAX was a CISC machine, and you had to have all this decoding, and it was a byte serial decode. VAX was overly complicated. For the reason it was overly complicated is because memory was so expensive when we did VAX that we wanted to encode, and PDB-11 was so wildly popular, we wanted to be able to encode programs in the same amount of space that we did on the PDB-11. So we created this instruction set that did that. But it was very hard to decode. So we started these RISC projects in several groups, and we had one at DEC West, and there was one, there were a couple of other ones, there were 3, I think, in the company, and finally we got to the point where the engineering VPs said, hey, we need just one of these, and we're going to anoint DEC West to be the keepers of the architecture, and that was the PRISM project. So I started to work on the PRISM project a lot like we worked on the VAX architecture, where we invited representatives in from various groups that would have to eventually support this thing. You know, the hardware engineers, the software engineers, and whatever. And we produced a couple different versions of the architecture. One was a 32-bit machine, and one was a 64-bit machine. And we were progressing along. We were building a new software system called Mica. You might have heard of Mica. Yeah. And Mica was wildly ambitious. It was at the level of ambition of Multics, maybe. I mean, it was, if we'd ever built it, probably nobody would have ever bought it. But it had a lot of good ideas in it. And anyway, we worked on it. And then finally, what happened was, you know, it's not moving forward at the speed I guess the company wanted, and MIPS kind of jumped up at the forefront of the RISC processors, and the VP of research was Sam Fuller at DEC, and he was sort of in Forrest Baskett. You ever heard of Forrest Baskett?
No.
Forrest Baskett was one of the principals in SGI, and he actually worked for DEC for a while at a place called WRL, which was Western Research Lab. In fact, they had a RISC processor called Titan that they did. Anyway, they were all touting the fact that there were companies that could build these one-chip systems that were faster than VAX. And so somebody stood up and gave a presentation that Ken Olson really liked, and the next day they canceled PRISM. And the day after that, I quit. But I didn't leave the company. I moved down the street, sort of across where Microsoft was, down on 520 for a while.
Yeah, I remember there were digital buildings down there right off 520.
And I was going to start a company, and I got 3 of the other guys that I worked on at DEC West. We were going to start a company, which was going to be a server company, and I spent a lot of time in Silicon Valley and talking to the VC people. We talked to Merrill Pickens. We talked to whoever John Doerr works for, Oak Investments, and a bunch of other ones. And we got money. We had money to start the company, and we're all signed up to start the company. And some of the people that had been at DEC West had left and went to Microsoft. And one of them was working for Nathan Myhrvold. And Nathan Myhrvold, we probably know Nathan. Mm-hmm. Nathan Myhrvold had had Bill's ear. And Nathan was very high on the whole RISC idea, and actually that was part of it. The other part of it was that all of the software that Microsoft produced that was operating system stuff was pretty pathetic. It was all assembler. It was non-portable.
Yeah, I wrote some of that.
You wrote some of that. So you know some of that, right? Did you know Tim Patterson?
No, I did work on DOS, but I mean, I'd met him, but I didn't know him well. So.
So anyway, you know, I get this call from Microsoft. They want to know if I want to come talk to Bill about a job at Microsoft. And I said, oh, sure. So I go over and I talk to Bill. And, you know, Bill is like, you know, you're going to take a job with us, right? And I'm like, well, you know, maybe not. Well, why? How can you possibly not take a job with us? We're the greatest people in the world. And I'm like, well, you know. So I, you know, listen to the spiel and talk to Bill. And the other guys go talk to him, too. One was Rob Short. You may have known Rob Short. Did you know John Balchunas?
No.
The other guy was Lon Willoughby. And so they all kind of went over and talked. And I came back and, you know, after all this, and we talked, and I said, hey, I don't see that this is going to be a great thing. You know, I'm not so impressed with Microsoft. And so I don't know whether I actually told them I wasn't going to accept the job or what, but Steve Ballmer calls up and says, how about breakfast at Denny's on Sunday morning at 8 o'clock? I said, sure. So we had breakfast with Steve Ballmer at Denny's at 8 o'clock. It's one on 148th. It's not there anymore. Right down from Fred Meyer's.
Yeah.
And he sold us. I mean, I don't know. That could have been Wednesday, and we signed up. I was there next Monday. I mean, it was that quick. So Steve was the one that really sold us all on going to Microsoft, and that's how we ended up there. And I've been a friend of Steve's and admirer of him forever. He's a great guy.
This is kind of a naive question, but Microsoft already had Xenix in-house, and they could have, in theory, built an operating system based off that, but they went and did a clean sheet design with OS2, and did that again with NT. Was it licensing or technical?
No, it didn't happen exactly like that. You know, they did the Xenix thing, and I wasn't there then.
Right.
They did the Xenix thing, and for some reason, they decided, the Xenix thing, there's one piece of the Xenix thing that was genius, and that was they had to get a license from AT&T. And so they said to AT&T, you know, would you consider doing a volume license for us so that as we bought more licenses that got cheaper? And AT&T says, yeah, we'd probably do that. And then Microsoft said, well, you know, like over $1 million, it ought to cost us like a couple of bucks or something. Yeah, that's fine. So what Microsoft then did was sub-license. They sold their licenses to other people and made the difference. They had a big business going, selling Xenix licenses. Anyway, back to DOS. DOS happened, and, you know, they chose DOS over CP/M, and there's a lot of stories about what went on there, about whether Digital Research, which was CP/M, got stiffed or whatever. But anyway, they ended with DOS. So DOS ships with the first PC, the IBM PC. And then they decide that you know, DOS is really this program loader. It's not really much else. It's just this program loader, and they really need something beyond that. So they decide they're going to do this joint design between Microsoft and IBM for OS2. And this is the 16-bit OS2. And they're going to do a new file system. And the file system was called HPFS. And Gordon Letwin, you know, is going to write the file system all in assembler and all this stuff. And they got joined at the hip with IBM. And the whole thing with IBM turned out not to work too well because IBM, a very old company, and the older a company gets, the more rigid they become, the more bureaucratic they become, the more risk adverse they become. So everything is like, specs upon reviews and mutual sign-off and everything. And the IBM guys are working in Boca Raton. The Microsoft guys are working in Redmond. And they're just not going anywhere with that. And so this story falls into Nathan saying, geez, RISC processors are the future, and there's no way that we're going to get, and 16 bits is not enough.
Right.
There's no way that we're going to port OS2 to anything. It's not portable.
Right.
We should build a system for a RISC system. And so one of the things that one of my things I told Microsoft was I would not work with IBM. I said, I'm not working with IBM. I said, they can comment on the design or whatever, but I'm not working with them.
And that was a fear of being mired down in their bureaucracy more than
it was like, if we just said, well, even if it as it was, they'd come in and they'd review every once in a while and produce the review comments, and they were super negative, and they actually split off and did a 32-bit version of OS2, which quickly went dove. We sent a copy to Lee Reiswick of that OS2. But we had the guys from IBM that reviewed the design of NT were AIX guys from Austin.
Okay.
You ever heard the name Larry Locks?
No.
Larry was their big honcho. He was their big honcho, and he'd come in with his cowboy boots on, and put them up on the table and pontificate. Anyway, so when we the charter when we started at Microsoft was a portable system that would run multiple environments. And the reason for multiple environments was that OS2 was going to be the target.
Yeah, what else would it?
POSIX.
Okay.
At the time, everybody was all hyped up about POSIX. POSIX was going to unify the Unix world. The Unix world started out unified because it came out of Bell Labs, and there's only one. But then the universities got a hold of it free, and every university had to put their widget in it.
Right.
And then everybody that got a hold of Unix after that had to put their added value on, so it became incompatible. So POSIX was an attempt to bring all this stuff back together. And of course, the other thing we had was we have CMU with Mach off on the side. So we wanted to have multiple environments, and we actually had, and the design of the system kind of was to be able to run these multiple environments. And we thought that the way to do that was to have the nucleus of the system would provide the basic services of the system, and then they could be customized for these different environments. Now, that's kind of a naive view because, in a sense, it's a naive view because there's a lot of things that wouldn't be very easy to do that with. Things like thread scheduling or stuff like that, it gets kind of sticky, and the process structure gets a little sticky, and paging gets a little sticky. But anyway, that's where we started out. And then, we get down the line, we're going along, and we spend about, 6 months to a year on a spec. And this is a pretty detailed spec, and it's 2 volumes that are that thick. The Smithsonian has a copy of those.
Oh, really?
Yeah, it's within the Smithsonian. So we produced this, and we start in on this project, and start actually doing things. And in the meantime, we have this Windows thing. And, I don't know, I don't think that Microsoft actually invented Windows itself. I think they got somebody somewhere had produced this windowing thing that ran on top of DOS, and we bought it from them, and we then shipped Windows 3.0. Actually, I probably wasn't called 3.0, it was probably called 1.0. Nobody cared. Then we shipped 2.0, nobody cared. We shipped 3.0, nobody cared. Then we shipped 3.1. They sold 16 million copies in 6 months. And Bill said, I think the main environment of our new system will be Windows. So that's why we went to Windows, is because of the acceptance.
Right.
Then on the other side was OS2 with the presentation manager. And I never worked with OS2. I can't say that. I never worked with it. I can say that, but I did work on it. We were developing NT on OS2. Even the ones that were targeted towards the RISC machines were developed on OS2. And we couldn't wait to dog food, to get off of OS2. It was...
So one huge misconception is what NT actually stands for.
Well, that, you know, the N10 was the i860.
N10 being the code name for the i860?
It was the code name for the i860. The i860 was a great graphics processor, and that's what it was really intended to be. It had a very unusual architecture. It was not operating system friendly at all. It had a virtually tagged cache. Virtual tagging of the cache means that every time you context switch, you have to flush the cache. Think about that for a moment, because the code that's flushing the cache is cached.
Right.
So it became very difficult actually to get all that to work right. The other thing it had was it had a floating point model. It was pipeline floating point. It was a pull model, though, where you actually had to pull things through the pipeline. Very funny architecture, but it worked well for graphics. It did not work well for operating system. But anyway, back to the N10 versus NT. You know, in the beginning, there may have been a few words about NT being N10, but NT really stood for next
new technology?
New technology. And, you know, we had big fights with the program managers because they didn't want, and the marketing people, they didn't want it to be called NT. They didn't want to call it NT because it stood for new technology.
Well, what's the old technology then?
No, it wasn't that. They said nobody will buy the system because it's new technology.
Oh, really?
Nobody will buy it. So we had a big fight about that, and I won the fight, and we called it NT. And I think that basically NT stands for new technology, but you know, there may have been some fuzzy piece in there where the letters N and T showed up because of N10, and we said, okay, that's a good, you know, it could be new technology. So anyway, I don't think it really makes a lot of difference.
No, just a point of curiosity. So were there 4 CPUs supported for the first version of Windows NT? Or which CPUs were in 3.1?
The first version of NT supported the x86, MIPS, and Alpha. No, wait a minute. Yeah, MIPS. It supported the R3000 of MIPS. I don't think we supported I don't think the R4000 was available. Actually, I guess it probably was. So it's the 32-bit x86, the R3000, R4000, and Alpha. And I think the PowerPC actually came in like 3.5.
Daytona, yeah. Or 3.5, yeah.
3.5. The PowerPC was by far the worst. IBM was really pushing the PowerPC. That was their new architecture. And of course, they had had such a success with the the original PC that they, you know, this is going to be their big thing. But they had all these other things that they sold, like AIX and their mainframes and everything. So they didn't want to cannibalize anything. Right. So they would never produce a machine that was actually competitive. And the tools, I think they did the compiler, and it was always broken. God, every day out of the build lab, we'd produce 4 builds or 5 builds. I guess it was probably 4 at that time. We could sort of dropped off the R3000. And every single day, the PowerPC build didn't build. Every single day. The RISC guys always built, and the x86 was pretty reliable too. And they kept doing that. And they never, ever actually got to a point where they had a competitive system. So eventually just dropped it. And they would revamp their systems about once a year. It's like they're not selling any, and we don't have the support yet. They're not selling it, and they're already revamping for the next one.
Right.
But it's always one level down from the other stuff that they're selling for AIX or something else. So that was a real experience with all those. And, the way we structured the system didn't really make a lot of difference in building it. It was just you just had the machines to build it. And of course we had to fix the different compilation bugs for ones. And then the machine independent code far outweighed the machine dependent code. So the dependent code is the processor specific code, and stuff that dealt with memory management and faults and exceptions and interrupts and stuff like that. So the majority of it was pretty well shared. So it all just kind of compiled and worked.
One question I get a lot is how much assembly is actually down in the HAL? Obviously, a lot of it's got to be system dependent, but how much of it actually needs to be in assembly language, if any? Well, some has
The
to be.
HALs are mostly not assembly language.
Okay.
There are, this is now, back then, there wasn't much in assembler then either. The things that would be in the HAL that would be an assembler that possibly didn't need to be an assembler were things that the compiler didn't do very well with, but they were very frequent operations that we wanted to make them run a little faster. Our philosophy from the start, I had witnessed the x86 compiler and the inline assembler and how bad that was. Basically the inline assembler, every time the compiler saw it, it just threw its arms up in the air and said, optimization, no optimization beyond this point. So I said, hey, we don't want that. So all the stuff actually I'm skipping here because I'm talking about 64 bits now, but this is a 64-bit thing. So we said, we want all of the stuff to be intrinsics. So all of those operations are intrinsics, which meant that all that stuff in the HAL could all be written in this C code with an intrinsic. So they might be a machine-specific intrinsic because the other machines didn't have those.
Right.
But the HALs, basically, there's hardly any assembler in the HALs. And most of the stuff that has to do with interrupt handling, which you might think would be in the HALs, is not in the HALs, it's in the kernel. Some of the stuff that's in the HAL that belongs in the HAL is like configuration hardware, like PCI space on x86s and x64, and then some other stuff for ARM is in some of the configuration stuff. The HALs, in fact, the HALs now, the x86 HALs we can build them now both ways where we can actually build them as part of the system as opposed to being a separate DLL. Originally, they were separate DLLs because they were beyond being a hardware abstraction layer. They were really a vendor abstraction layer.
Okay.
So there's the HAL-specific stuff, but we imagined that vendors were going to build HALs, which was a bad idea.
On their own, yeah.
And we did have some vendors that tried that. We had a couple of MIPS vendors that tried building their own HAL and didn't do a very good job. So they've become basically just part of the operating system. And I wish we would have built them that way in the beginning, is just another directory that produced an object library that we just linked in. But we couldn't in the beginning because these had to be pluggable because we had one basic SKU with different vendors being able to ship the system with their HAL.
Sometime around after the original release of NT3, or in the original NT3.1, the video driver ran in user code. And there was a parallel tracking thread on the kernel side.
Well, yeah.
So there was a fair bit, not a fair bit, it was a certain amount of overhead that we backed out for Daytona. But now I'm wondering, are CPUs fast enough that that performance difference is still relevant?
Oh, yeah. I mean, today, a lot of the stuff in the GPU is dedicated towards not just graphics. And GPU performance is right at the top. And this, in that time, we had a 64 KB window. That's what was shared. Today, that would have to be 64 gigabytes.
Right.
I mean, it's like, it's not scalable. We worked very hard to make this thing work in user mode and to make it so it was okay as far as performance was concerned. And we were pretty good with it. And I was really against moving into the kernel mode because I didn't figure that the guys that did the graphics stuff in the user interface, user 32, could really write, that really knew enough about writing high quality code, and I was right. We moved it into kernel mode, and we found out all these things that didn't quite work anymore. Right? Like the synchronization model is, when you're in kernel mode, everything's parallel, and it's parallel. And the only way it's not parallel is explicit synchronization. And in user mode, that's not true. If you know that you're the only thread, then you're the only thread no matter how many processors there are, then you're the only thread. And you're safe. You're thread safe, so everything's great. So there was a lot of growing pains, and it wasn't simply, let's just pick up this set of code and move it down here into kernel mode. There was a lot that went with it. And the other thing that sort of hampered that too was that all of that old rotten 16-bit code was still in the code. Imagine. So that all got put in, drawn in. And so it wasn't that we had 16-bit code, we had 16-bit data structures and 16-bit primitives that were still there and had to deal with those. Now those, I think, are pretty much gone now. In fact, the whole structure of all that is different now. It's not the same. The video drivers don't fit in the system exactly the same. Of course, that's went through, I don't know how many different models, of the way that works. And I can't tell you which model they're on now, although I am right now working on graphics. There's a lot to it. Anyway, it was a good move. I didn't think it was going to be a very reliable move, and we've gotten the reliability to the point where it's much better. We had a lot of problems for a long time with vendors supplying graphics drivers.
Right.
And the graphics, they think that everything's great, and we just show them the bug data from the field and say, here's your NVIDIA driver. It's got 20,000 bugs against it. Really? It fails, on the average of once every day and a half or something. Really? So all that's gotten better.
Earlier you mentioned the Friday whims. What's a whim and why do you have them?
Well, when we started out, when I went to Microsoft, we took 12 people. Well, we immediately hired 12 people. And we had a hardware group and a software group. One of the things for going to Microsoft was we're going to build hardware. We decided we're going to build the first RISC PC, and we did. We built the first RISC PC. In fact, we built one with Olivetti with the 860, which Olivetti dearly wanted to ship, and we finally said, no, you're not shipping this. So we wrote this big spec. We spent all this time, wrote this big spec. So all these 12 people that are on the software side of it are all busy doing all this. But eventually we got to the point where now we're going to hire people and kind of fill out the group. So one of the people we hired was Dave Thompson. You remember him?
Yeah.
So Dave was in charge of the network group, and this is probably more than a year into the project, maybe a year and a half. And he came up with this idea that we're hiring so many people and nobody knew each other, and that we ought to have some way to get them together. So he said, we'll have something called the WIM, and it's the weekly integration meeting. All right, so every Friday afternoon, there was five managers that worked for me. One of them would go down to the Safeway and buy a few cases of beer, a couple of shopping carts full of chips, some shrimp and whatever. And we'd take one of the hardware labs and open it up and invite everybody in to meet everybody. And that became very popular. We started out in a room that was probably about the size of this. And we ended up with having these things and then it kind of moved from there. Remember building 1 and 2 had this reception desk and sort of a reception area. It moved to the reception area. And then we got Marriott to cater the things, and nobody was going to Safeway anymore. And this happened, this was like every Friday night, virtually for the time from we started that until the time we shipped 3.1. This happened every Friday night. And one of the things that I really was displeased with Mr. Zachary Pascal with, which I'm sure you've read the book, was that whole book was about how we tortured people and the death march and everything, and we never gave them any respite or anything, which was absolutely untrue. We tried very hard to knock that edge off every week. That's where WIM came from.
All right. So I enjoy as much open track time as I can get, but you actually went all out with actual competitive racing, open wheel, and everything. How did you get into that, and why did you get out of it?
Well, I think it's when we shipped 3.1. Steve Wood had this brilliant idea. You remember Steve? Mm-hmm. He had this brilliant idea that we should go down to Laguna Seca and enroll in a race car driving course. So I think about, somewhere around 15 people. We all sign up for this course and we go to Laguna Seca. And I think it's a 4-day course, and it's in Formula Fords. And I can't remember that course as being particularly inspiring. The cars are slow. They're open wheel cars, but they don't have much power.
Okay.
And they're clunky. They're really clunky. The transmissions were clunky. But anyway, we did that, and then we found out that they had another course that was in a different car, which was powered by a Mazda engine. And these were pretty spiffy cars. I mean, they go 130 miles an hour. So a bunch of us signed up for that and did that. And so we did that, and then we found out that they had. So that was a lot more interesting, and that was a lot more challenging, satisfying, whatever. It was something that you really had to focus on and concentrate on, to be good at and really practice at. It just wasn't something you just don't jump in a car and go off and start turning record laps.
Right.
It doesn't happen.
Well, the main thing, too, is while you're doing it, you're not thinking about your taxes or your girlfriend or whatever. No. You're considering, you're focused entirely on that one process.
And it's even tinier than that, because you're focusing on in front of the car and what's coming up next. What happened 10 milliseconds ago or 100 milliseconds ago in the last turn, it's gone forever. Never going to see that again. The only thing you might remember out of that is if you did something wrong.
Right.
And then you're not going to do that again, right? So anyway, we did the Vance course, and then found out they had a racing school. They had a racing. Well, they had a race. I guess it's called school, and it's basically you sign up for 2 days of racing, and then they have. It seems like we had a practice day. It was Friday, Saturday, and Sunday, and on Friday you did like a couple sessions on the track, like 2 half hours or something, and then you did a race on Saturday and you did a race on Sunday, and then they had 12 of these. I think there was 12. I don't know, maybe there was. Yeah, I guess there's 12 because there's 2 weekends. So I did that, and then I sort of like, geez, you're looking for a little more speed or whatever. So they have what they call the pro race. And what they do in the pro race is it's the same engine, but they sort of take the governor out of the picture and open up the exhaust a little bit, and they go a little faster. And the other thing they let you do is screw with the suspension. So you get, this whole thing is built around a mechanic school. So they're charging you to drive their cars, and they're charging these mechanics to train them how to fix the cars. And you're paying for all the crash damage and everything that happens to the cars. So I did a pro race, and I got to be really good friends with one of the instructors, Case Montgomery. And so he's talking to some guy that had raced in Atlantics, which Atlantic car is a Formula car, open wheel car. Do you know what a Formula Atlantic is? Mm-hmm. Okay. So once upon a time, they had a series that actually raced in Canada, the U.S., and Australia. And there was a car in Australia that had been stranded there and only been raced once. And he got the instructor all hopped up about buying this car and bringing it back and racing in the Atlantic Series in the U.S. and wanted me to know if I'd be interested in, being involved in this. And I said, yeah, sure. So I ended up buying the car, and he raced the car in 1996. And the next year, we decided we were going to buy a new car for him. And so we had this old one. And it's old in the sense that the body work is different. It's a refinement of the aerodynamic of the body. The engine's the same, the transmission's the same.
Right.
So it's not like it's just drastically different. So this series at the time had 2 classes within the race. There was the C series, and then there was the guys that were racing for the big buck pros, big bucks. It's called your bucks, So I said, well, I'll try to drive the car and see if I can do it. So we went down to Firebird. You know where Firebird's at?
No.
Huh? It's in Phoenix.
Okay.
Firebird is actually on an Indian reservation, and they have 2 race courses, and then they have a drag boat course. Bondurant Driving School is headquartered there. So anyway, we go to Firebird, and my driving against the instructor's driving, which he's been now in the Atlantics for years, I'm only off by 2 seconds in his lap time. So they sell me on the fact that I ought to race. So that's the start of my racing career, which was 1997. I did 56 races. My last race was at the PepsiCo Center in Denver, and we raced all over. We raced in Houston. The street course there. We raced in Florida at Homestead. We raced in Nazareth, Pennsylvania. We raced in Toronto. We raced in Montreal. We raced in Trois-Rivières, which was by north of Montreal. We raced in Vancouver. I did Vancouver several times. We raced in Portland. We raced at Laguna Seca. We raced at Long Beach. We raced at Mid-Ohio. Raced at St. Louis. Raced in Chicago. So I did 56 races, and the last one was in PepsiCo. And I was sort of like, I was 60. That was when I quit when I was 60. This is 2002. So it's a few years ago. And I was sort of at the point where every year I got better, and every year everybody else got better. But they got better faster than I did. So I became more competitive, and so my best finish was, I finished 8th at Milwaukee. Oh, I forgot Milwaukee. The Milwaukee Mile, the oval. The ovals I was very good at. The street courses and the road courses I wasn't as good at. But the ovals, the younger guys don't got the cajones, right? You know, there's only 2 kinds of oval racers. Did you know that?
No.
There's the ones that haven't hit the wall, and there's the ones that have. And the ones that haven't are going to hit the wall. So eventually you're going to hit the wall. And I had 2 big wrecks on the wall, one in St. Louis and one in Phoenix at PIR. That was just testing. Anyway, that's how I got in. And I got out because, you know, I sort of was at the point where I'm pretty old for to be doing this. There's nobody else 60 doing this.
Right.
You know, they're all 19, 21. You know, I thought a little bit the cost was prohibitive. It was tremendously prohibitive. The way to make a big fortune in racing is to make a small fortune in racing is start with a big one, not racing.
Right.
But the other thing was, this took up a lot of time. You know, we travel on Thursday and get home Sunday night. And we had 12 races a year. And then you couple that with testing, and we do at least 6 test days. And test days were, usually a test day was a test weekend. So we would arrive on Friday and test Saturday and Sunday. So I just kind of got worn down.
Let's see. After Daytona, do you remember Bob Day?
I do remember Bob Day.
So I and Bob Day and a couple of guys did the port of the Windows 95 user interface over to NT. And we got it running on the NT 351, basically. And that was sort of integral to the Tukwila project. And it was helpful in killing off Cairo, but I didn't get to go to any of those cool meetings. So what actually happened in those years in behind the scenes?
You know, what happened was they hired Alchin. And Alchin came from Banyan. And Bill was big on Alchin. And Alchin had these grand ideas about building this user interface in Cairo and everything. And Windows 95 had been brought out that interface and was pretty popular. And, you know, we wanted to bring that over to NT. And it's, no, we got to take it to Cairo. And so, you remember Megan Bliss?
Mm-hmm.
Megan Bliss and I convinced Jim Alchin that we could do Tukwila and Cairo at the same time. That we had enough lab horsepower to do that. Of course, you know, I don't know why he bought this story, but he bought this story. We said, here's what we'll do is, you know, we'll basically still have the 2 groups. We'll have the Cairo group, and we'll have the Tukwila group. He didn't like the name Tukwila. And the T-shirt, I don't remember the T-shirt. It says,
I was going to wear it tonight, but I said
it says Tukwila. It's just down the street a ways, and we know how to get there.
We can get there from here. Yeah.
We can get there from here. So the deal was that every day we would put priority getting a Cairo out of the build lab first, and then we get the rest of it out. And it turned out that every day Tukwila just came out every day. And Cairo was always broken.
Right.
It took forever. And little by little, the Cairo features didn't get done. And they never, one of the things we did with NTFS, we said, you guys can change the file structure as many times as you want, but you can't stop people from booting old systems and using old file structures. You have to either do an upgrade in place or you have to accept the old stuff. We're going to be dog food on this file system. The OFS guys never did that, right to the very end, and they kept promising and promising. So they didn't get all of the burn in.
Right.
And eventually they missed a date. They said, OFS is gone. I say, that's gone. So little by little, these features, they just never delivered. And they just never delivered. And Tukwila just kept growing and growing and growing. And eventually, the only thing that I can remember that we really brought over, actually maybe two things. I think we brought over the file server software. I think that replaced the NT one. And the other thing we brought over was Kerberos. Those are the only two things about Cairo. Everything else was junked.
Really?
Completely junked on the floor. It just wasn't there. The people, I can't really, I guess I shouldn't really say anything. There's a lot of good guys that worked on Cairo. And I just don't think that the whole project had the focus and the desire to make it really great. And it just fell by the way because, you know, on the other side of the fence is the NT group, and they're not letting up. They're full on the throttle. And Megan did a great job of selling all this. I can remember the day we did this with Alshan. We're in one of the conference rooms in Building 36, and said, hey, we'll just do, Tukwila will just be a backup. It's just the backup. NT40, I think, is still one of the most popular ones that ever sold.
Yeah.
I ran into somebody, I don't know, a couple of years ago that was still running NT. They still had NT40 running on something. They still loved it.
Yeah, I've got it on a Model 95 over there.
Yeah.
The big IBM tower. But scheduling software is notoriously hard, of course. And the original version of Windows was supposed to take 2 years or 3 years. I forget what was estimated, but it took longer, let's say.
Which one? Windows NT?
Yeah.
Yeah. It was supposed to be 3 years, I think, 2 years. We did VMS in 2 years.
Right.
But in VMS, there was some difference. In VMS, we had probably the whole project had 20 people, and that included the compiler people. And the main thing, the tools there was the Fortran compiler because we were selling that as a Fortran machine. But every single one of those people were, you know, really just top-notch people. And so it was a very, very talented group, extremely talented. And we did not have that with the NT group completely. I mean, we had a good core and we had great people, but it wasn't as small a core, and we had to do more stuff.
Right.
So, and then of course we had some other things in there too, where, you know, we threw out the 860, and then we started on MIPS, and then Digital came along and said we want to do the R3000 in addition to the R4000, and then we decided we're going to do the X86, all before 3.1 shipped. So originally it was just going to be one architecture, and we're going to do the system for it, and we end up with all these architectures, and actually throwing out the 860, which was a godsend because that would have never. I mean, it was so bad, it was terrible. There were the errata sheet, I swear it was a half-inch thick.
Really?
Oh, it was everything. And Intel would come and say, they'd say there was new errata discovered. You know, floating point something doesn't work. No problem, though. The Intel exception handler handles that. Well, we didn't use the Intel exception handler because it was so buggy, it didn't work. So anyway, that's how Tukwila came about and how Cairo ceased to exist.
All right. I think about the time I started, There was a famous incident where you punched a wall and they framed the hole.
I did.
But I don't know what that's about.
That was at the 25th anniversary. I brought in I still have that.
The drywall?
Yeah, that was NT System 52. That was an argument that I was having. We were having some stressful moments about the debugger and the debugger not being very functional. And work didn't seem to be progressing very fast, definitely not progressing at the speed that I thought it should be progressing at. And I was having this argument, I think it was with Brian Willman, in one of the corridors in Building 2. And I said something, or he said something that really ticked me off, and I wham like that. It's a good thing I didn't have 2 before. I hit between and they're metal, you know.
Yeah.
So I hit between them, and yeah, I went through the wall.
So I'm fortunate that a lot of the code that I wrote back in the day still lives on in the code today. And I don't know how common that is. How much do you think of NT 3.5 is still in Windows 11 today?
A lot.
I mean, it's growing a lot, but the core piece is still...
Of the original code, of the same functions that the original code did, I would say, you know, it's 80%.
Okay.
It's very high.
Right.
But there's a lot of added stuff.
Yeah.
There's a lot more stuff added around security. There's a lot more stuff added around management. There's a lot more stuff added around just building the system. You know, what you remember of build is gonzo. I mean, it's become a system of its own.
Really?
So a lot of it's still there. You know, the kernel code, the memory management code, Landy, you know Landy Wang, probably. Mm-hmm. Landy manages to probably pretty much rewrite memory management about once every 3 years. But there's a lot of memory management functionality that's new, that's all been done since then. But the basic structure and the basic code from the beginning is still there. The process structure is still there. The kernel's still there. There's been a lot of stuff added around. There's some stuff added around fairness and scheduling, and some other things. And of course, there's more objects. I think one of the things I think made NT such a good code base was the object manager, and that has not changed. If you look at Unix, you know, everything's a file. You want to extend the operating system? Create a new file system. Not a good thing.
Right.
I mean, you can even read papers that some of the grand poobahs of the academic world say, you know, maybe we were wrong. Maybe everything isn't a file. Anyway, creating object is easy. You know, you just have to build an object type descriptor, integrate it into the object manager, and presto esto, and write a few services, and there it is. You have a new object. And that object can provide synchronization. It can provide a lot of things, right? So I think that was just a really great underlying structure that went into the operating system that's lived on. You know, we've rewritten a lot of things. The handle table has been rewritten several times. I don't think we've done that lately, but you wouldn't think that handle translation would be a performance thing, but it is. Mm-hmm. It's a real performance thing. And you know, typically you run a system, like my system at work runs with, I don't know, like 60 processes and, you know, I don't know, a couple hundred threads, and 150,000 handles are open. That means there's 150,000 objects in the operating system that are being tracked. They all have security. You'll have access protection. So anyway, a lot of the code is still there, but a whole bunch of stuff keeps getting added. A lot of stuff. So of the original code, I bet you the original code is not a large percentage of the total code.
Right.
If you took the total code
Yeah, no, it's going to be a small, tiny percentage.
Because it keeps going down.
Yeah.
Because all this stuff gets added.
But it's like the one thing I always like to use as an example. The original Task Manager compiles to 85K, and now it's 4 megabytes, and it does more than it did, but not that many multiples of times better.
The Task Manager, my system, I have two AMD Ryzen Threadrippers, and one of them is smaller than the other one. The small one is 64 cores with 128 threads. The other one is 96 cores with 192 threads. You should see what the Task Manager puts up for the per CPU utilization. It's unviewable. I mean, you can't. It's just all it's all these little boxes with all these things going up and down.
Right.
You can only really look at the overall performance, or if there's no option to say, take this group of 8 over here, put those together and sort of.
I think you could heat map it or do some kind of visualization that was useful, but
there's also a lot of other things too. There used to be on the Task Manager used to be the network stuff and the CPU stuff, but now there's disk and there's other stuff. So
people often ask about Longhorn, and I believe that was the precursor to Vista, or became Vista, or it was along the way to Vista.
Well, there's a big story behind that.
Okay, let's hear it.
So when we finished Windows 2000 was done on the same code base as, the workstation and the server were the same code base. So we went off to plan the next system. And the guy that's going to do the workstation is Chris Jones. And the guys that are planning the server is Dave Thompson's group. And they come back and say, Thompson says it's going to take 3 years for us to do the next server version. And Chris says, oh, I can't live with that. He says, consumers don't expect the quality that the server people do. We can do it in 1.5 years. So we said, well, we can't do that, right? So thereupon, we split the code base. The server went one way, and the consumer vision went the other way. It wasn't long before the consumer software hardly would build and hardly would run. In the meantime, the server branch, we fixed a whole bunch of security problems.
Right.
A whole bunch. And we might have even done some security update, but there was a lot of stuff that went into the server effort to fix security bugs, and none of that stuff was fixed in the other one. Well, we finally shipped XP, and XP was wildly successful, but it was buggy. But then there was a big turmoil about security, and that's about when the buffer overflow attacks started. Right. And so we stopped. And in fact, the other thing was, as soon as they shipped XP, that became the code base for Longhorn, which was Vista. So they're continuing on with this buggy code base without all those security fixes in it. The server division basically is developing the server stuff but fixing security problems. And in the meantime, in the middle of this, sort of somewhere in here, I start this project that's off on the side that is the x64 stuff.
Okay.
So AMD comes in and talks to us, and he talks to Rob Short and I, and says, we have some ideas on how to build 64-bit extensions to the x86 that will be very less intrusive and will allow us to run 32-bit applications at speed on the 64-bit machine. I said, geez, that's pretty interesting. what have you got? Well, we got just a few ideas. And we said, well, go away and come back and tell us what you want to do. So they come back and we look at it and say, this is great. This is great. I mean, it's like unbelievable. So I said, hey, we're going to do this. So we just set out to do this. This is not a company-anointed project at all. And I say, we're using the server code base, and we're going to produce a 64-bit workstation, and we're going to produce a 64-bit server. In the meantime, we got Longhorn over here still going. And its name is now morphed into Does It Matter Horn.
Right.
So it becomes Does It Matter Horn. And Alston, of course, he's my boss, and he's running Longhorn. I mean, he's responsible for that. And I'm running this x64 thing. And the server group is they're off, they're shipping a system. And we're just using their code base. Well, we build, we get the x64 system running well enough, we get everything ported, and we have a simulator that allows us to simulate setup. And we simulate setup. It takes 24 hours. 24 hours. The simulator is called SimNow. And AMD finally ships us a system. It arrives at 12 noon. And they say, there it is. And we got a CD. And we walk over to that machine, plug the CD in, and boot the 64-bit system. The first time it's ever been tried, and it boots and runs, and it doesn't fall over and bug check. So this sort of piqued the interest a little bit at that point, and we get reliable enough that we actually convince Microsoft.com, that website, to switch over to our 64-bit server. And they run it, they only have to run it in about a week, and they switch everything.
Really?
And you know why they switched? It was so immensely more reliable than the 32-bit stuff. They just switched like that. And the reason was that their software, I got cramps in my legs. The software has got so many memory leaks in it that on the 32-bit system, they keep leaking memory until eventually they got the virtual memories all filled.
Right.
And then they have to roll over. The 64-bit system, it took a long time. So we had Microsoft.com running on it. So we got to a point where the guys just couldn't get Longhorn or Does It Matter Horn out of the build lab. And I tell Alston, I said, this is baloney. You guys should switch the code base to the x64 code base. And eventually that's what we did.
So you unified them back again, so server works
all the
same.
I left out one thing. We stopped in the middle of we didn't actually stop the 64-bit effort, but the 64-bit effort is mainly, we're just porting stuff to get it to run 64 bits. And we didn't have to port everything. It was much like back in the days of VAX where all the 30-bit stuff just ran. Your task manager just ran. Didn't have to change a thing. The only thing that changes in the task manager was where it said what your process list was. I put an asterisk in so it could tell whether it was a 32-bit or a 64-bit one. It's the only thing we changed. So in the middle of this, though, the security of XP got so bad we had to actually stop and fix XP bugs. And we fixed a lot of, my group fixed like 5,000 of those. And we went through everything, and we turned over some code that, like a shovel, you turn over manure. I think the worst code I probably looked at was the IME code that was done in Japan.
Oh, okay.
Just terrible. Like, just no regard for any bugs at all, and any bug condition, they just, oh, okay, that's bad. Okay, well, just skip that then, just keep going. So there were actually overflow bugs we couldn't fix. We just couldn't fix them. We tried to mitigate them as best we could, but we couldn't fix them. But anyway, there was a release of XP that was an update that was like a 250 megabyte
Okay.
dump. And then they switched the code base for Longhorn to the x64 code base. And that's the code base we're on today.
And everything is still unified now?
Everything's unified.
What about the stuff that went to Xbox? I don't know much about Xbox technically, but I know that it runs a hypervisor that's similar to what goes on in NT. Is there code shared or just ideas?
Well, the hypervisor for Xbox came from Red Dog. And Red Dog is the hypervisor that was developed for Azure. When we shipped the 64-bit system, we shipped it on Thursday. I quit. I sent mail to Bomber on Friday, said I quit because it was so bad. I had such a problem. I couldn't get any traction on FCIBs. Do you know what FCIB is?
Do not.
An FCIB is a fucking checked-in binary. And the reason that it's called a fucking checked-in binary is because we had all sorts of groups at Microsoft that checked the binary in rather than the sources. So it made it very difficult to port stuff. And it was stuff that was in the product.
Right.
And so I was so fed up with not being able to get support from Bill to obliterate this stuff and say, hey, you guys have got to get your sources in. You don't have to port it. We'll have somebody else port it, but you got to get your sources in. So I quit. And I'm gone Bomber sends me mail and says, I don't think you ought to quit. Why don't you take some vacation and think about it? So I answered and said, okay. That was March 28th of 2005. In November 2005, it started to the weather was bad, so I didn't have anything to do anymore, so I came back to work. And I think February I went to work on Azure. And Azure was the premise. Azure was sponsored by Ray Ozzie, who was the software architect of the company. Do you remember Ray? Probably not.
Ray Ozzie?
Ray Ozzie?
By name, but that's about it.
Anyway, Ray looked around and we had all these properties that were producing cloud-based stuff, but there's no infrastructure, platform infrastructure to work on. How do you deploy the applications? How do you do configuration control? What version is running? How do you do restarts and all sorts of stuff? So he talked Bomber and Gates into starting this project, which was called Red Dog, which eventually became Azure. And so this was going to involve virtualization. So this is at the same time that, we bought a company called Connectix.
Right.
And Connectix came to Microsoft with two products. One was called Virtual PC and the other Virtual Server. And they had started development of a hypervisor, and we actually took where they were at that time, which they were very embryonic, and we built a hypervisor to bring Azure up with. And when I left Azure to go to work on the Xbox, the Red Dog hypervisor became the basis for the Xbox hypervisor.
Okay.
All right. So the Xbox, the structure of Xbox is we really run three different copies of operating systems. We run just three VMs. Like in Azure, we run hundreds of VMs. You spawn VMs, you spin them up, and Azure was all about the platform and building all the infrastructure to provision new machines, bring them online, keep track of them, do the billing, the cloud file system, just all that stuff. It was called PaaS. And we thought that everybody that was what they wanted. In what AWS was serving up was IaaS, infrastructures. So on Amazon, you actually bought basically a virtual CPU. We were saying, we're going to sell you the stuff that allows you to deploy things, right? You can deploy a an operating system, and you can deploy your applications and keep track of them and do billing and all this stuff. So anyway, stepping back to Xbox again, we're only running 3 VMs. We have 2 VMs that run all the time. One is the host system. The host system owns all the devices. So all the hardware access to devices is in the host system. The host system is also sort of the traffic cop for any communications between the VMs. And we have formal communication between the VMs as opposed to Azure, where there's the only communication between VMs would be where you had actually a network connection to somebody through a VM. You know, you don't have anything where you're not close as an operating system. So we have one OS that runs basically what you see is the presentation.
Right.
You see the windowing system, the window manager runs there, and that one's running all the time, and the host system runs all the time. And then we have a game VM, and the game VM starts and stops all the time. A game is a VM.
Right.
So games got packaged with an OS. So, and this is a feature and not a feature. It's a feature in the sense that you never have backward compatibility problems, because you say, here's the OS that you can package your game with, the current version of it, and it comes in a GDK, which is a graphics development kit. You develop and package your game with that stuff in that development kit, and when we run your game, we run that VM with your game. So it always runs. We will never obviate your game by some change in the operating system. That sounds great.
Hard to update stuff.
Huh?
Hard to update stuff too if you can't modify it later.
You can't. The update, you can do an update to your own stuff, and you have a choice. Your choice is you can stay on with your old. The place where that didn't work, and we actually ended up producing a universal game operating system for stuff that was prior to this latest Xbox, what do we call it? Xbox X, I think? Not X. I don't know, whatever the console came out about 5 or 4 years ago. Yeah, maybe it was.
Sure.
No, it was always called Xbox One.
Yeah, Series X would be the newest, right? I think.
Yeah.
Is it Xbox One's the new one?
I don't have one. I don't know.
Anyway, we came across a thing that we wanted to add a feature that was a very important feature for selling systems. And we had to find a way to get that feature into these old copies of these games.
That's what I meant by updating the existing. Yeah.
Well, I thought you meant update like bug fixing. The bug fixing is like, if you want to put out a bug fix thing, we fix bugs on these GDKs, but you package your game again.
Oh, okay.
All right? Your old one doesn't get the bug fix.
Okay, that makes sense.
If the guy's running the old one, he runs the old one. All right, so this thing we did was, it's called pause resume. So on the Xbox, it takes forever to load a game because there's so much data. I mean, there's gigabytes and gigabytes of data that come with it. There's texture data, there's image format stuff, and all just a bunch of stuff. Well, pause resume allows you to do basically a save of the VM and then bring it back later. So we had to get that into these systems. So we produced this universal one. And the universal one's kind of interesting because one of the things we'd done was the original NT had the capability for drivers to create system service dispatch tables. And of course, some of them did. And of course, our original graphics, our game VM had its own. And then several other releases had modifications to that. So this universal OS has to translate all of the system service call numbers according to what the version is of the, the game was packaged with. Anyway, that's kind of besides that. Anyway, that's the way the game runs. So, you run a game, and then you can just let it pause, or pause, sleep, or whatever while you're not running a game, or you can start another game. And if you start another game, then you actually kill off the VM and start another one. So we started out with the host system is Windows 8 based, and we wanted that to be as minimal as we could make it. So that one's really custom. It's been hacked down, but the basic structure, the object manager is still there, events and all that stuff are still there, scheduling is still there, drivers fit into the system the way they did in circa that. But there's a few more things that are there that allow for communication with the other VMs or cross VM stuff. So that's Windows 8. The one that has the display, basically the window manager, is based on the current version of Windows.
Okay.
And it's based on it, right? And we don't really... There's some stuff replaced and stuff left out. In the operating system itself, there's a lot of conditionals, conditional compilation, to take out things that we just don't want in the Xbox operating system.
Okay.
And so on the mirror of that, which is the VM that the games run in, is also Windows 11 based. And it's almost identical to the other one. One of the things that's different is they both interface with the graphics driver, but it's not symmetric. It's not uniform. One side uses the Windows 11 stack,
okay,
and the other side uses a very highly customized DirectX stack. So that's a little different, and that's just mainly to make the graphics for the games run better.
So going back a little bit, a long ways back to high school, I told you had collected 16 varsity letters.
I did.
Is that really 4 varsity sports per year, every year for 4 years?
Yes.
Which 4?
I did track, baseball, basketball, and football.
And did you go to college on an athletic scholarship?
I had 3/4 of my scholarship base was athletics and 1/4 was academic.
And then at some point, now I have a senior of my own who's quarterback for the team, and he just blew out his appendix in week 2, so he's got 4 weeks off. So he knows a little bit about the dreams deferred, but you damaged your knee at some point, did you not?
I was playing football. Actually, my first injury was, what was my first? My first injury was in football, and I broke my leg. And I broke my fibula in October of my sophomore year. And I actually ended up playing half of the game on a broken leg. The doctor we had was the team doctor this is 1961, 1962, and not the kind of team doctors you necessarily have today with medical expertise. So I came over to the sidelines. My leg really hurt, and he's squeezing my ankle and saying, does this hurt, that hurt? And I said, no, it's okay. And he looks at the coach and he says, do you really need this guy? And the coach says, oh yeah. He says, okay. So he opens up his case and he gets out a hypodermic and gives me a shot. And so then they tape everything all up. And they say, okay, go up and run down the sidelines. So I, tried to run up down the sidelines, and I said, this doesn't feel good enough for me to play or to run.
Right.
And the doctor looks at the coach again and says, you really need this guy? And he says, yeah. So he gave me another shot. So I went and played the rest of the half. And then at halftime, this stuff wore off, and so there's no way I could play in the second half. So the doctor says after the game, maybe we should go down to the hospital and get this x-rayed. So it was just a break in the bottom of the fibula. It's just, it seemed like it took forever to heal. But anyway, the following spring, I tore up my right knee playing basketball.
Okay.
And in those days, anything that happened to your knees that even smelled of cartilage, they said, we got to take the cartilage out. I mean, today, they don't do that.
Right.
They go in there, and if you have torn cartilage, they might sew it up. They might trim it up a little bit. Arthroscopic surgery didn't exist then.
Right.
So they ripped out my meniscus in my right knee. And I came back the next year to play, and I went through all the preseason practice and everything, which all happens in August, and this is in Michigan where it's just excruciatingly hot. And we get in the first game, and I tear up my left knee. Same thing. So here I am, within about 10 or 12, 11 months, I've had a broken leg and 2 knee operations. And I came out the next year to play again, and I'd had all this time where I'd been on crutches for the broken leg and everything. And not being able to walk, you kind of take walking as for granted. It's like, I can walk,
Right.
Well, when you can't walk, it's like, geez, I don't think I want to do this the rest of my life. So the doctor did an exam on me, and he says, God, your knees are really weak. And I don't know. This is the team doctor again. So he scared me enough that I said, hey, I'm through. I'm not going to play anymore. So I didn't play after that.
So what happens on an athletic scholarship if you can no longer play? Do you risk your scholarship or not?
In those days? In those days, the scholarship was good for the whole thing. And this was a Division III school, and the scholarship situation was very funny because they didn't really have scholarships or athletic scholarships. They had something called grants and aid. And a grant and aid could be given to any student. So I had 3 grants and aid for the 3 sports. I only played 3 sports in college. I didn't play 4. And I had an academic scholarship, and my academic scholarship was such that I had to have a B average at the end of 2 years. And at the end of the 2 years, the only semester in my whole college career, I had a B- average. So they took my scholarship away.
Really?
Yeah. Anyway.
So you've played for a lot of teams. You've probably played for a lot of different coaches. Is there anything about any of those teams or coaches that informs the way that you run a software team today, or that informs what you expect from the people on it?
Well, I had one coach, which was the second coach I had in high school, that was sort of somebody that I really looked up to. His name was Bob Dilday. He was from Michigan State, and he played quarterback with Tommy Usick. If you remember Tommy Usick, you probably know.
No.
Tommy Usick was one of the great quarterbacks from Michigan State, and he was a real hard-driven, want-to-win kind of guy. And I think I sort of, that really was something that I kind of was attracted to, and I really looked up to him. Unfortunately, he wasn't there my whole career in high school, because I think I could have done a lot better, because he pushed people and got a lot more out of the people. I'm all for. I'm not somebody that wants to drag people up. I want to motivate people to do what they ought to do, right?
Right.
So, and he was one of those kind of guys.
I think you have a saying somewhere that is, successful people do the things that the unsuccessful people typically refuse to do.
Yep.
Any good examples of things like that in daily life as a software engineer?
Well, I think that saying kind of came from people who, they say, I only write the code, I don't test the code.
Right.
Or they say, I don't care if the schedule says we're going to ship 2 weeks from now. I mean, at 5 o'clock, I'm out of here. And so I learned very early at Digital that if I wanted things to happen, that I had to make them happen. And that might mean that I did a lot of things. I might be fixing bugs for other people. I mean, people hate to fix their own bugs. And that's another thing. It's like people don't want to fix bugs. It's like, I wrote the code. It's good enough. We'll shake all this out in testing. Well, I'm not a believer in that. I'm a believer that you should do the best you possibly can do, and then we'll find the ones after that, and it'll be even better. So I think it's this thing about doing whatever it takes to make things successful is what I really mean by that.
Right.
It's not necessarily a specific part or any part that would be the most glamorous part of what you're doing. Like somebody saying, I'm an architect. Well, it's like Fred Brooks. Fred Brooks says there's thinkers and there's doers. He says thinkers are a dime a dozen. Everybody can think great thoughts. Doers are rare. Thinker-doers are rarest.
Right.
Right. So, we need people that are architects that think, but they need to have a view of they got to do more than just think. Right. They got to make sure that whatever they're doing is actually going to meet whatever goals or constraints that are put forward for whatever they're architecting.
So your first major job out of college was at DuPont, working on a project for Scott Paper. Is that close?
Scott Paper, yeah.
Yeah. And you were using a computer, and at some point the computer became far more interesting than the paper project itself, I'm guessing.
Yeah, I graduated, the school I went to was a liberal arts school, and they were religiously affiliated with the Congregational Church, loosely. Although in the early 1960s, it was much stronger than it is now. It's hardly any relationship now, but I didn't have any idea what I wanted to do. And a lot of things about college were like, I went to college basically to play sports. I didn't go to college because I had some vision that I wanted to be anything. I just wanted to play sports. And this was a place that I could play sports. And I couldn't afford to go to school anywhere. So I could get there and do that. But I got real interested in math, and I got interested in physics. And I spent most of my time in math and physics in college. So when I graduated, one of the things I liked to do was I worked summers building barns. I built pole barns.
Okay.
And I ran the crew to build pole barns for this company at the age of 18. So I like to build things. So I thought, I'd really like to find an engineering job. So I'm looking for an engineering job. And I'm sending resumes to the aerospace industry, and everywhere. Nobody wants anything to do with me. So I sent this thing to DuPont, it said, hey, here's what I'm interested in. I got a response. So they invite me down there to interview them, and I go, and it was a life lesson I learned. And what I did there was I accepted a job there without really knowing what the job was I accepted. So here I thought I was gonna work on testing methods for elastomeric materials. Well, what I was going to work on was documenting testing methods for elastomeric materials, and English was not my strong suit at all. And we had three different organizations that had to approve test methods. We had manufacturing facilities. We had the place that I worked, which was a sales service laboratory. They helped customers use our products. And then there was the research group. So they all tested these materials. So they wanted standardized testing. Well, all of them had their editors. So they would all edit this stuff. And I don't think I ever got one approved, not one. But there was a group there that was a math and stat group that did math and stat analysis of customers' processes using our chemicals to build products. And Scott Paper Company had invented this process to make foam, which was centrifugal casting. Foam, if you've never watched foam made, it's magical. It's just magic. It's usually made, well, back then, I'm sure it's not changed much. There would be a conveyor belt that's just flat and goes on for as far as you can see. And it's maybe 6, 8 feet wide. And they shoot paper out onto this, and it's kind of crimped up on the sides. And they have a mixing head at the front of the one end of this, and this goes around continuously on a belt. And the mixing head takes 2 chemicals, just 2, and they put them together, and it mixes these 2 chemicals and pours them out on the paper, just back and forth like this. So it's this puddle. Within about 20 feet, this has risen to be about this high. It's just magical.
Right.
And so at that time, they were making, this is a time when, I don't know if you remember, there was a time when we went through where a lot of garments that were outdoor garments had foam insulation in them.
Right.
Well, that was made out of these things were cut up into 60-foot long, what they called logs. So you imagine you have this thing 6 foot wide, 4 feet high, and 60 foot long. And now you got to make a sheet of this so they can use it in textile and stuff. So they would take this stuff and cut it up into, that was called a bun. They cut this up into what they called logs, and logs are like maybe 1.5 feet square and then across, whatever, 4 foot across. Then they drill a hole through them and put them on a mandrel so they could spin them, and they'd spin them on a mandrel and with a slitter and peel off a long sheet. And that's what they used in the textile stuff. Well, Scott Paper Company decided that this was too much waste because you have to knock all the corners off and you just throw them away. So they decided they'd try to invent centrifugal casting. So they invented this machine. And this machine, you know what a caged roller bearing looks like?
Yep.
Well, think of this as a caged roller bearing that is like 30 feet long and about maybe 5 foot in diameter. And setting on this big thing at an angle and spinning, and it has rollers in it. There's rollers all around in it. There's some drive somewhere that's driving this thing, so it's going like this. And at the top of this, they shoot pieces of paper in that are about this wide with some glue on it, so it glues. And they have a mixing head with a pourer. And they pour the foam down into the top of this thing like this barrel, and it spins. And as it travels down, it does its thing, and it expands. And they had, at the other end, they had like a buzzsaw saw that sawed these things off into 15-foot chunks, what they called zarks.
Okay.
So a zark was a cylinder with a wall thickness of about like that. And the thinking was that they just put that on a big mandrel and spin it, and they'd have none of that knocking off the corners.
Right.
So I got enlisted. Well, the math and stat group asked me if I would be interested in working on a computer simulation model for this process, what they were doing. And I said, sure. I was so bored. I mean, they could have asked me if I wanted to be the janitor, and I would have probably said, yeah, that would be more interesting, what I was doing. So I said yes. And so we decided we're going to do this in a discrete simulation language called GPSS3. And if you're familiar at all with discrete simulation? Yep. Okay, so it's like it's a time interval thing, and the clock just jumps. And each interval, there's some set of discrete events that occur. So off I go to Poughkeepsie to go to the IBM GPSS3 school, which was quite an experience, and learn GPSS3. And there's people there. I remember there are people there from Otis Elevator.
Okay.
They're doing a simulation of the algorithms they're using to send elevators in high-rise business offices.
That's what we simulated: elevators and traffic lights.
Right. So I come back and I go up and I meet all the people at Scott Paper Company, and they have an intern they assign to work with me. We're going to sort of work together on this thing, and I'm going to develop the model, and I'm going to try to, transfer whatever knowledge I have of the model to him, because after I'm off of this, he's going to be on it. So I start developing this model, and the language is like a flowchart language, where you have little boxes, and little boxes do certain things, and it's all sequential.
Okay.
Basically there's no real parallelism in it all. So it's a sequential thing. And so you connect all these things together just like you're drawing a flow chart. In fact, you draw a flow chart to represent your program. And then you take your flow chart and you punch up each one of these boxes as a certain encoding on a punch card. And you basically put them in the computer, and it doesn't really compile anything. I think you can think of this as it's just recording of this big piece of data. It's a data-driven simulation. So this is more than the data. This is actually the logic. So it's sort of like a program, and there sort of is things like things like go-tos and things like that. And so I developed this model, and I'm happily doing this. And I had, in my life, I'd never worked on anything that was really exacting. If you're building a barn, if it's eighth inch off, that's nothing.
Right.
Even a half inch, okay, you could cover that up. But somehow, things like key punch errors and things like that just didn't go through the computer very well.
Right.
Well, this was all unknowns to me. And so finally the day arrived, the IBM representative and my boss and the guy that I worked with at work at DuPont and the guy from Scott Paper Company were all going to go to the data center in Philadelphia to run this GPSS3 program on their 7044. So off we go, and we get there, and you can't imagine the madhouse of being in the data center where all the time is scheduled. There's no sharing of anything. Everything there's a little timestamp machine. You grab a piece of paper, you go over and you get it stamped to your start time. They'll tell you when your start time, or tell you when you can go on. You go over and you punch this thing, start time. You run over to the computer and, do your work, and then you run back over and stamp your thing. So, we go through all this, and we go to the computer, and we load up the deck of cards and everything, and spin the tapes and the whole works, and, it reads about 10 cards and rolls over dead. What's wrong? And it turns out I got out of my model is I would say about 1,000 cards, 1,000 statements, and I probably got 500 errors. We spent the whole day trying to fix the errors and never got them fixed. We'd create more errors.
Right.
And so, that was the first experience. That was the most humiliating day, I think, of my life. I just thinking about how can I possibly make this many errors. So we went back to DuPont, and I decided that what I was going to do was, we had a compute service there at the engineering department that was an 1108, which was a UNIVAC machine. Well, actually, it was 1107 at that time. And my group, which is this math and stat group, said, well, you can run Fortran programs down there anytime you want to. So I decided I'm going to write this Fortran program that's going to look at all these cards and get rid of all my errors, all my key punch errors. So, and in those days, not very many people really punched their own cards. They just corrected
Right.
So you write all this stuff up, and you send it to the key punch, and key punch would punch it all. One person would punch it, and then another person would verify it all. And even after all that, there were still all these errors.
Right.
So I write this program in Fortran, this program must have been the most god-awful looking program ever written by man, that actually went through and found all of the problems, and now we could go back to the data center and run again. So you go back to the data center, and now I'm dealing with logic errors, and we're going back and forth, and somewhere in this process, I decide that I'd like to know more about the machine. Compilers really baffled me at that time. Like certainly the machine can't take in this text and do something with it. What's going on here? So I decided I'd learn something about the machine, so I get a 7044 assembly language manual, and one of the blocks, these things were blocks that you had symbols for in the flowchart, was called a help block. In a help block, you could write your own code. So I'd say, geez, what can I dream up that I've got to have a help block for? So I had when I ended up, I had about 1,000 card help block, all 7044 assembler. And somewhere in there, I decided that I was really more interested in the computers than solving problems with computers.
Right.
So that happened in like 67 or somewhere along there.
So correct me if I'm wrong, but I'm guessing that even the original release of NT was too much for any person to keep in their head in detail, or was it still compact enough that you could understand the whole thing at that time?
I think that it was compact, that you could understand you understand the concepts of how everything's working. It definitely was big enough that you couldn't have the code all in your own, nobody could know all the code.
Was the move to Xbox in any way a desire to work on a smaller, more self-contained system that you could have greater control over? Or just good opportunity?
I was really bored with Azure. We got to the point in Azure where, the hypervisor was working, and we did a lot of operating system work there in the beginning because we had a host system there, and we didn't use Hyper-V, and we didn't run Windows in the host system, and eventually Azure has actually replaced the original hypervisor with Hyper-V, and they've replaced the host system with a standard Windows system. But at that point, we didn't have any plans to do that, and I was just sort of bored, and so this opportunity came up to go do this, and I went and listened to what they're doing, and I got a chance to look at this. One of the things I got a chance to look at was what became HoloLens, and some of the embryonic stuff of that.
Right.
But at that time it was, you required this big tether, on a big cable off your headset to the server computer to run all this stuff but it was fantastic graphics. 3D was unbelievable. Anyway, it was mainly to have, I was looking for something to do.
So I think there's a tendency with programmers to, the first time they attack a problem, they don't know what they're doing yet, so they write a terrible version of it. The second time they think they understand, and they make a super complicated version of it and over-engineer it. And then the third time they scale back and figure out what they were really going to do in the first place and do it right that time. Do you have any sense of that progression from RSX to VMS to NT, or are they all pretty much locked in for the time that they were in the market? Or let me put it this way, if you had to rewrite any of them now, would it be significantly different?
Probably not. RSX 11M was definitely not an overextended system. I made a stamp up that says size is the goal.
Right.
And I stamped everything with size is the goal. So it was very constrained. we had to run in 32K bytes of memory. And in 32K bytes of memory, you had to be able to run the file system. You had to run the Fortran compiler.
Right.
You running their linker. So it was extremely constrained. VMS was constrained too because there was the time that we basically had to do it was going to be short, and we were really this is the first system we were going to introduce paging into, and even though the PDP-10 PDP-10 did not have paging, it had swapping, and all of the hype of about paging just wasn't very good. It was the paging systems basically didn't work very well, and we spent an awful lot of time on VMS trying to make sure that we did things in a way that the paging would be good. One of the problems we had with VMS was very small page size. That didn't help. So VMS was constrained by the ship date, so we didn't have any grand ideas. One thing that we did do with VMS was, we thought we did, was we looked at Unix for a little while and tried to pick the things that we thought were good features in Unix and bring them into VMS. And I don't think that anybody would ever say that they thought any feature in VMS looked like Unix, but
right.
NT would probably be the one that maybe we were a little bit more optimistic about. However, there's one thing in the middle of this that maybe saved NT, and that's Mica. Mica was very grandiose, extremely grandiose. And one of the things, in fact, it scared the hell out of me, that we'd ever be able to build it. It was very complicated. It was designed by, like, I don't know, a dozen and a half people in a room together. And a lot of people that were on the design team had almost zero experience with actually building an operating system. So, everybody that's a user thinks that, well, everything should be it should be a service, an operating system service. It's like, and not thinking of it in terms of, well, is that something that really belongs in the operating system, or is it something that belongs in a subsystem, or something that belongs as a library or whatever? And so they tend to gravitate towards features that just shouldn't be in the operating system at all. So we had a lot of arguments about that. But Mica probably helped trim down NT quite a bit. The whole object architecture in Mica was extremely Baroque. And it was a multi-level architecture with containers and protection at each level and access controls and all sorts of stuff. And after having done NT and finding out that the handle table translation was so important, I mean, it would have been like, that would have been just a disaster. Yeah, real disaster. So no, I don't think any of them were over grandiose. I think NT is proven itself to be very malleable, very extendable. We keep hitting security problems, but the security problems are different. I remember back with VMS, we tried to, at the end of VMS, we tried to build what was called an asecure VMS system. And it was a single user system. And it ran excruciatingly slow. But the level of things that were considered to be security issues then are not the same as they are now. I mean, the stuff now is the worst problems aren't the problems that are bugs. It's the problems where there's some phenomena that sprouts up because of the hardware or some way that people find to use the hardware in a way that lets them break the system. The recent example of this is I guess you probably would call these hardware bugs, but the bugs where there was something called the threshold bug.
Okay.
And threshold was caused by this is an Intel only problem. It didn't happen on AMD. All these processors are doing a lot of speculation these days, and they're executing way ahead. And on Intel, when they hit an access violation, they just put a set of bit that said, okay, this is bad, and let that keep right on going. They just kept right on speculating. And then sometime later, that instruction tries to retire, and it says, oh, it's bad. And now what they have to do is they have to unwind everything. And they unwind it all. That's good. Everything's cool. And except for one thing. They allowed software to access variables that weren't in the cache that were accessible after having discovered an access violation.
Okay.
So that gave people a way to decode things by looking at the timing. AMD did not have that problem. AMD, as soon as they saw the access violation, they said, that's it, and cut them off. So there is a problem that was a security problem that caused a lot of upheaval. The latest one is this one, which they're all side channel. A lot of this stuff lately has been side channel stuff. This is where you do something here and you do something and somebody can infer something from that. But they don't have a direct channel of the data, but they discover what the data is based on a side effect of what you did. And this has to do, this particular one has to do a lot with what's called the branch target buffer.
Okay.
And, you have branch prediction, and branch prediction predicts branches. But the branch target buffer predicts where the next instruction is. And you'd think, how in the world could that work? Like they keep this cache of where the next instruction is going to be. They access the cache, and if it looks legitimate, they start, that's where the next instructions come from. Well, you can cause a leak of information if you can figure out how the branch target buffer works and kind of preload it, and then ask the operating system to do something, knowing that what it's going to do with that speculation that you've loaded into the branch target buffer in such a way that you can get cache timing information, which then you can translate into data.
Okay.
That's Spectre. So the security problems have changed a lot. And, on Xbox, Xbox is to our knowledge, has not been broken. That doesn't mean it can't be broken, but we had a team that twice tried to break into Xbox, and they actually got in. And the way these guys, they just have a different mindset and the way they think about things and making things do things. Typically, they'll find a bug, and a bug that doesn't look like it's disastrous on the surface, but it turns out that it gives them enough information that they can cause something to occur. And then they do something that writes over the stack, and you do a return. Writing over function variables is a popular one. Of course, all of these things that we try to mitigate all these things in the operating system. Anyway, I don't know how we got down that path, but...
Well, I got two good questions left. One, I don't know if we can talk about it yet, but one thing that always fascinated me back in the day was Lego or BBT. And it was...
BBT?
Yeah. And the reordering of code in order to get jumps to be more predictable or closer. And better locality of cache reference and everything else. And it seemed to have a pretty good performance impact on binaries. Is that a public tool yet? Is that something other people can run on, or is it still an exclusive Microsoft technology?
I think BBT is still Microsoft. I mean, I'm not absolutely sure. I don't think we run BBT on as many things these days as we used to.
I guess memory pressure is not the same as it used to be either. So,
well, BBT was basically reorganizing things so that you get all the stuff that you don't execute out of the way.
Right.
And the stuff that you do execute, you have together. I don't know how much stuff, the Windows stuff, I don't know how much is BBT, but I think it's still, it's a significant performance thing. It's like 5%. I just haven't been involved. We do Pogo now too. We did, when we did BBT, Pogo was kind of there's a couple things.
I don't know what Pogo is.
Pogo is profile guided optimization.
Okay.
So basically, BBT does profile. You could call that profile guided optimization too, but it's being done by a tool that's run over the binary after the fact. And, it has to keep up with all the stuff that they do to change the format of the binary and stuff that's in the binary and whatever. Whereas the Pogo is done by the compiler. So Pogo can ingest the data from the profile into the compilation of the code and produce code based on that.
Okay.
All right. The other thing that I don't think that we had at that time that was as well developed was whole program optimization, link time code generation.
Okay.
All right. So, basically we mostly compiled objects, and then we linked objects together. And now we mostly compile into this intermediate language that then gets ingested by the linker, which then links the whole program and does optimization over the whole program. So I don't think BBT is as important as it used to be, but
okay.
I can't give you a definitive answer on that.
Okay. Oh yeah, I had a new guy start for me, and first thing he has to do is enlist in the source tree. So right before lunch, he does I think it was just a straight enlistment, but we got back 45 minutes later, and we could hear his phone ringing down the hall. And I just kept ringing and ringing and ringing, and we get there, and I say, "Oh shit, Dave C's on the caller ID. What do I do?" And I said, "You better answer it." And I think all you said was, "Release your fucking lock," and hung up, and because he had locked the source tree and gone for lunch. So.
That doesn't sound like you at all, though.
Well, at that time, we had a source control system we endearingly referred to as slime. And it was slime.
Yeah. It didn't do forks. It didn't do anything. It was
the problem. That was the original Unix source control system.
Oh, was it?
It's RCCS. They decide they're going to build this source control system without really building a client server system. So they say, how are we going to do this? Well, say we have remote file system access and we have file locks. We'll just have the client lock the file. So that works fine until the client fails while holding the lock.
right.
And now the whole source control system is down because this one guy, his system crashed. And when he recovers, he has no idea that he held the lock.
Right.
That's why we had all these people that were status file repair experts. I don't know if you remember those guys.
No.
Chuck Lensmeyer was one. You remember Chuck?
By name, but
I would all the time calling him up saying, could you unlock this file? It was on a per file basis, so it wasn't like they locked the whole thing, and it was slow. It was excruciatingly slow. You remember Dave Snip?
no.
He was actually at the 21st anniversary. He was in charge of printer drivers, and he was a neat guy. He left Microsoft and went back to England, and I think he was from England, and started a company that does, I think it's sound and lighting control for concerts.
Oh yeah.
Great guy. Anyway, he'd run Slime, and he'd have like 10 or 15 copies of it running at once, because that's the only way he could get any speed out of it. Terrible.
We had the streamlined utility for copying the kernel. Suck. I remember that. Better than the fast utilities.
Well, Gordon Bell was definitely a mentor for me. My coach in high school was definitely a mentor for me. Other than that, I don't think I really have any mentors. I mean, I never had anybody that, I could go cry on their shoulder or
Right.
whatever. Those events were more than a couple of years apart.
Yeah.
I mean, I still see Steve once in a while and go to the basketball games with him, now that he owns the Clippers, and play golf with him once in a while. Not very often, but he's still. I worked directly for Steve for many years. I started out working for Steve when I first went to the company, and then they shuffled me over to Paul Moritz. And then the one I really didn't like is when I got shuffled to Alchin. And then from there, I went to Azure, which was totally different. Wasn't any of those guys. And then I think when I went to Azure, I went back to reporting to Steve. But by then, Steve is like the CEO of the company. So I'm hanging off of his organization here. I never go to any of his meetings, never see him, but I report to him.
Sounds ideal, really.
It was ideal. Well, when it came out that he was going to leave, I sat down with him and said, "Hey, we got to find somebody to be my boss, because I don't want to end up in a situation where the new CEO comes in here, and of course he's going to have to go around and glad hand all of his direct reports. He's going to come and glad hand me, and then I'm not going to show up at one of his executive meetings, and he's going to wonder why I'm not there." I said, "We got to find somebody that's in the know here, right?" So we did, and I worked for somebody else for a while. And now I work for Phil Spencer, who is the VP of the Xbox division.
Okay. How big was your org when you finally went individual contributor? What was the biggest org when you had all of NT?
About 450. I did that after NT 4.0.
Okay.
I said, I don't want any more of this. I mean, everything was growing at a prodigious rate. And everything really took off with NT at NT 4.0. That's when we began to ship a lot of systems.
So in a company like that, is there a big downside to not being an empire builder?
Well, I think it comes down to where your talents lie.
Right.
If you've got good currency that's outside of that, I don't think it makes any difference.
Yeah, good point.
But if you don't, then you better find if you want to grow like that, you better find somewhere where you can go, where you can actually do that.
Right.
That's, I think, the reason I had the limited success I had with race car driving as late in my life as I did it was just being able to focus on what you're doing.
So when you code, can you multitask, or are you a one thing at a time kind of guy and don't distract me? And
Well, I'm sort of like, I think multitasking is good, but I think that the highest productivity is not multitasking, because it does take some time to context switch.
right.
I do multitasking because there'll be a problem somewhere that I'm not working on, and that somebody had a problem, and I'll go try to fix it or whatever. But in general, I'm working on, one thing. Right now, we're trying to get in the game VM space. we're running a Linux VM. And we're running a Linux VM there to be able to take advantage of some of the spare cycles we have in the data center with the consoles we're running there in something called xCloud. Have you heard anything about xCloud?
No.
xCloud is basically taking Xbox consoles, repackaging them into a rack, and putting them in the data center and giving people remote access to them. So that allows them to play basically the AAA rated games, the really high performance, high graphics resolution games. Well, but they're single tenant systems, right? One person can be playing one console. Right. So you have to have a lot of them. And so there becomes a question about what to do about the duty cycle of those, because people don't play 24 hours a day.
Right.
So there's a bunch of idle time. So our plan is to run AI and machine learning workloads that are Microsoft specific on those systems in the off hours. So that's what I've been working on. And it's the first part of that was to get Linux to run with the Xbox hypervisor. And then the second part of that has been to get the graphics stack running. And it seems like I've been working on this forever, longer than VMS. So, you know, the University of Washington built a new computer science building a few years ago.
Yeah.
And I made a donation to the thing, and they're going to name a room, actually a laboratory after me. And I said that I'd do that, but I wanted them to put a slogan on the wall in the laboratory. This is a big lab. This is probably maybe 50 by 50, so it's a big lab. And the slogan is, if you don't put them in, you don't have to take them out.
Yeah, it's hard to do, especially when you're younger and just starting and haven't paid the price and having to fix your own shit.
When I started, the debugging tools were so bad, that I don't know how anybody could have that philosophy at that time, because it was so hard to find a problem. I mean, really hard.
I'm working on this Kim 1, which is a single board 6502, 64K flat model, but there's no debugging, there's no printfs. It's got a hex keypad as pretty much your entry point to it. And so when you write code for that, you have to be excruciatingly careful because the turnaround time is immense.
Right.
But once you get the simulator on the desktop, then it's like make, run, make, run, make, run. It's very easy to go back and forth, and it totally changes the way you code. So
the tools that we use today have become so functional that, and a lot of the stuff that's been done has been aimed at trying to cut down on some of the little errors that people would make that aren't made. They aren't like logic errors. They're just errors that they make because they're just they're not their attention to detail isn't good enough or something, and so a lot of that stuff's gone. So I would say that there's not as much emphasis on quality as there was when you were working with these machines, where there's like basically sometimes, the only way you could do anything is with a scope, a hardware, a logic analyzer, and you're looking at it and saying, oh, well, yeah.
I was looking at an old Burroughs. I think it's a Burroughs, and they had all the scope hookup points right inside the door because you're just going to have to always resort to it, apparently. So
I never worked on a Burroughs machine. I did work on that Bunker Ramo, which was kind of a funny machine.
What about a Bendix? Have you ever worked on a Bendix? No? That's vacuum tube days. That's getting old. But
that was before me. Bendix was a drum machine.
Yeah.
That was the main memory was drum, I think.
It wrote and rewrote.
It rotated,
the
and the way you put your program on the drum was to try to make it so that when you finished the instruction execution, the drum had rotated to pick up the next instruction.
Yeah, well, they're all written on this drum, and the drum's spinning at 3,000 RPM or some incredible speed. And
those drums, the Bendix drum, probably wasn't that fast.
No, I've never seen one running. They're always crashed by the time I've ever seen one.
The 1108 had some drums that were just unbelievable. They were word addressable. They had 3 tracks per word. Word was 36 bits. So they're pulling off 12 bits in each track. It was a 7,500 RPM disc, or drum, and it was canonical. So when it spun, it rose up like this to the heads, and if it lost speed, it dropped so that they didn't have head crashes. And it was just lightning fast in those days. This was in the late 60s. I don't know what the access. Oh, the minimum access time of those things was like 3 milliseconds or something like that. That was minimum. Now maximum was a full rotation.
Yeah.
So, and today it's like everything's SSDs today. So there's zero.
Right.
It's whatever the SSD's time is. So, boy, does that make a difference.
Yeah.
How much vacation time are you taking these days?
About the same as I've always taken. You know, I take about 6 weeks a year, probably. Basically, I'm either on vacation or I'm at work.
Yeah.
Or I'm riding my bike. One of the three things. So we have a place in Hawaii. We try to go to about 1 week a month through the winter.
Oh, yeah.
And then the summer is here. So, and I'm still working. And I don't know what I'd do. If I had a garage like this and interests that you have, then I'd be not working.
Right.
But I don't. So I'd be lost at home. I'd like, what am I going to do? Did you ever get a chance to go down to the Living Computer Museum?
I did. I saw it before it closed. It was really impressive, especially because everything runs. It's not just a static display. Or at that time, everything ran.
Rob Short and I were down there one time and they gave us a private tour. And they had at that time, one of the basement floors was absolutely packed with equipment. They had a lot of deck systems, a lot of old PP8s and PP11s. Some 9s, some 15s. I don't remember seeing any VAXs, but I really like that museum and the fact that they closed that, and it doesn't look like there's any real plan to reopen it.
No, I've tried to find out what's going on, and I haven't been able to find out anything. So, I guess he didn't fund it. Paul and his sister.
He didn't fund it in his will, apparently.
Yeah.
And which is funny because that must have been just an oversight that he didn't do that.
But he didn't do it with his movie theater, and he didn't do it with his other thing that he had. So it seems like he didn't make any plans, which is weird.
Well, I like to go down there and look at those old machines. And you know, the computer museum, the computer history museum now is all towards whatever is the state of the art now, and what people are interested in computing now, and I like to look at the old stuff.
Yeah.
And say,
I'm doing an episode on IBM hardware, so I went down to the Computer History Museum in Mountain View, the one you're a fellow at, or your picture's on the wall anyway. I remember that.
That's got to be the Computer History Museum then.
Yeah, which one were you talking about?
That's what I was talking about.
Local here or down in
No,
Mountain View?
down there is a Computer History Museum.
Oh, okay. Here
There-
is a living computer museum.
And this one up here is the Living History Museum.
So I've been to both, yes. Oh yeah, so I went through and I filmed all the old, the 1104 and all the old IBMs along the way, and I'm going out to Poughkeepsie in 2 weeks to see what their current state of the art is, because I haven't been in an IBM data center in 30 years, so I have no idea what they're making. But I did an old episode on PC versus mainframe and what the fundamental differences are, and I think I joked that I wish IBM would send me an old System 360 or something for the shop, and they actually called and they were talking about the power requirements are a bit much, and they're 3-phase, and figured out you could actually run it, but it's easier to just go and tour what they've got rather than. My buddy down the road, he had a shop here, and he just had a big 1-phase motor spinning a big 3-phase motor, and it would spin the three-phase motor backwards, and the leads came off it, and it ran his mill and all his equipment. Worked fine, so surprised me. But
Well, there's a lot of interesting old IBM stuff. I would be most interested in seeing some of their old stuff like Stretch.
yeah,
And some of the stuff, the 709.
704, some of those machines. I did work on the 7044, which was sort of an offshoot, I think, of the 7094. Anyway, they're all 36-bit machines. All those original machines were 36 bits.
Why 36? Is that what you need for precision when you convert
It was
to floating point?
it was floating point precision. IBM came out with the 360. You know, they came out with a 24-bit mantissa with a hidden bit. The 36-bit floating point did not have a hidden bit.
You mean the implied first bit or whatever?
Yeah.
Yeah.
It was not hidden. So the mantissa was the mantissa, period. And the IBM system came out with a hidden bit, which gave them one more bit of precision. But 24 bits is still pretty slim. And even, I mean, people complain about 64 bits, either range-wise or precision-wise, one of the two.
Maybe you try it.